Alright, hello and welcome. I'm going to pick up from where we left off the other day. Oh, excuse me. Excuse me. So yeah, can I win? Is the question. We were looking at this yesterday and I got stuck. Couldn't come up with an answer. So I said, alright, we're going to revert to Sprague-Grundy theorem. Now we're going to go ahead and take a look at competitive programming algorithms for some information about Sprague-Grundy. I think what I'm going to do is I think I'm going to split my time from studying the articles on this website and solving the Leetcode problems, because I think if I do that, I read one of these articles one time, then solve a problem, then read an article, solve a problem, read an article, solve a problem. I think I'll get to a point where I'll be solving the problems really quickly, because basically if you get stuck on a problem, it's probably because it's related to something on this list that's not trivial. You wouldn't be able to think it up on the spot. You kind of would need to know these things already and be able to apply them on the spot to do it quickly. So yeah, I know a lot of these things already, but I don't know all of them, And one of the ones that I don't know, at least I know of it, but I can't easily apply it, Sprague-Grundy, which is what we're working on right now today. So let's read the problem so that everybody has an idea what's going on. In the quote-unquote 100 game, two players take turns adding to a running total in any integer from 1 to 10. The player who first causes the running total to reach or exceed 100 wins. What if we change the game so that players cannot reuse integers? For example, two players might take turns drawing from a common pool of numbers from 1 to 15 without replacement until they reach a total greater than or equal to 100. Given two integers, max choosable integer and desired total, return true if the first player to move can force a win, otherwise return false. Assume both players play optimally. So this looks like a game that we can apply a Sprague-Grundy theorem to. Its theorem describes the so-called impartial two-player game. So it's a two-player game. Whether or not it's impartial, we'll get to in a second. Those in which the available moves and winning losing depends only on the state of the game, which is true, right? So it's impartial, depends on the state, whether or not you're going to win or lose. The only difference between the two players is that one of them moves first, right? Additionally, we assume that the game has perfect information. No information is hidden for the players. They know the rules and the possible moves, which it is in this case. Assume the game is finite, which it is. A certain number of moves. One of the players end up in a losing position, which they can't move to another position. On the other side, the player who set up this position for the opponent wins. Understandably, there are no draws in this game, right? So it's all of those things, this game that we're looking at. Such games can be completely described by a directed acyclic graph. The vertices are game states and the edges are transitions moves. Vertex without outgoing edges is a losing vertex. The player who must make a move from this vertex loses. Right. So there's sort of like ending game states in your acyclic graph. Also, the left side of my neck, it's like, I don't know what's going on over there. I kind of noticed it yesterday. I don't know, today I'm noticing it too. I'm wondering if it's how I slept or how I've been sitting or if I've been doing something wrong with my neck here. I don't know. But anyway, so, okay, can be described by a directed acyclic graph. Since there are no draws, we can classify all game states as either winning or losing, right? So the game state, yeah, you're either going to win or you're going to lose, right? Because the state that you're in, you're either moving towards a winning state or moving towards a losing state. Winning states are those from which there is a move that causes inevitable defeat of the other player, even with their best response. Losing states are those from which all moves lead to winning states for the other player. Summarizing, a state is winning if there is at least one transition to a losing state, and is losing if there isn't at least one transition to a losing state. Yeah, or you could define this a few different equivalent ways, but yeah, what they gave is sufficient. Our task is to classify the states of a given game. The theory of such games was independently developed by Roland Sprague in 1935 and Patrick Michael Grundy in 1939. NIM. This game obeys the restrictions described above. Moreover, any perfect information impartial two-player game can be reduced to the game of NIM. Studying this game will allow us to solve all other similar games, but more on that later. So, super interesting. Basically, that's what we're going to do, right? That's the approach we're going to take with this question, this medium question. Historically, this game was popular in ancient times. Its origin is probably in China, or at least the game Jiangshi is very similar to it. In Europe, the earliest references to it are from the 16th century. The name was given by Charles Boutin, who in 1901 published a full analysis of this game. NIM. Okay. Yeah, really interesting. Game description. There are several piles, each with several stones, and a move player can take, and a move a player can take any positive number of stones from any one pile, throw them away. A player loses if they can't make a move, which happens when all the piles are empty. The game state is unambiguously described by a multi-set of positive integers. A move consists of strictly decreasing a chosen integer. If it becomes 0, it is removed from the set. So yeah, NIM's pretty interesting. Basically, yeah, you got piles of stones, and you can remove as many stones from a particular pile as you want. And then the last player who can't move loses. So basically, if a player is looking at empty piles, they lost. So yeah, NIM's a super interesting game. A lot of fun. Well, I wouldn't say it's a lot of fun. It's actually, you could actually prove that NIM is the first play. I think it's the first player always wins if he plays perfectly, something like that. Yeah, there's some maths involved with NIM where, or actually we're going over that right now, but you can basically either always win or always lose if both players play perfectly, and that's provable. So, I guess it's not that much fun of a game, but I guess the mathematics of it is fun. That's fun. As I said, there's a question on Project Euler that I solved related to NIM. It's a variation that you can use Sprague-Grundy to solve it very quickly, I believe. The solution by Charles Earl Boutin looks like this. Boutin, I don't know if I'm saying that correctly. Boutin. The current player has a winning strategy if and only if the XOR sum of the pile sizes is non-zero. The current player has a winning strategy. The current player has a winning strategy if and only if the XOR sum of the pile sizes is non-zero. The XOR sum of a sequence A is A sub 1, XOR A sub 2, XOR dot dot dot, XOR A sub n, where XOR is the bitwise exclusive OR, or the symbol. The key to the proof is the presence of a symmetric strategy for the opponent. We show that once in a position with the XOR sum equal to 0, the player won't be able to make it non-zero in the long term. If they transition to a position with a non-zero XOR sum, the opponent will always have a move returning the XOR sum back to 0. Yeah, so, yeah. Prove the theorem by mathematical induction. For an empty NIM, where all the piles are empty, i.e. the multiset is empty, the XOR sum is 0 and the theorem is true. Okay, that's base case. Suppose we are in a non-empty state. Using the assumption of induction and the acyclicity of the game, we assume, so this is, by the way, the directed acyclic graph. This is a significant, important part here. We assume that the theorem is proven for all states reachable from the current one. I'm kind of wondering now, I'm thinking about, well, never mind. Okay, just hold off on that. We assume that the theorem is proven for all states reachable from the current one. Yeah, right, that's what it means by induction. Mathematical induction, all the other states that you could reach. That's already true. Proof splits into two parts. if for the current position the XOR sum is 0, we have to prove that this state is losing, i.e. all reachable states have XOR sum that's not 0. If S is not 0, we have to prove that there is a move leading to a state with t equals 0. Okay, so let me just think about this for a second. So what they're saying is, if the XOR sum of all the piles is non-zero, then you can win. The symmetric strategy is that if there's an XOR sum with all zeros, then, or that's the XOR sum that's 0, then you're going to lose, right? These are like sort of, we're proving these things sort of at the same, we're using the same, sort of this same idea. So we want to prove by induction that if we're in a state where we could have two options for our state, right? So let's say we're in some state, either the XOR sum is 0 or it's not 0. If it's 0, we need to show that we can get to a state that's not 0. If it's not 0, then we need to show that we can get to a state that is 0. And I think it's also, yeah. Right. So that's pretty much it. Is that there's always, from 0 there's always a state that's non-zero, and from non-zero there's always a state that is 0. And how do we prove that though, right? So assume the theorem is proven for all states reachable from the current one. The proof splits into two parts. If for the current position the XOR sum S is 0, we have to prove that this state is losing, i.e. all reachable states. I'm so confused, I'm sorry. I'm doing it wrong. I'm not. I mean, how many times have I actually proved this, right? How many times have I actually proved this? Yeah, you gotta practice these kinds of things. Let me back up. So, okay, in order to be a losing state, what does that mean? That means that all of the transition states that you're going into are all losing states. In order to be a winning state, that means that any of the transition states are a winning state. Okay. At least one is a winning state. All right. So we want to prove that if the XOR sum sequence is non-zero, then there's at least one transition you can go to that the XOR state is also non-zero. If and only if the XOR sum of the piles is non-zero. A winning strategy. And there's a symmetric strategy for the opponent where once you put the opponent into an XOR sum where that's 0, sorry, yeah. So there's a transition to a state that's losing for the opponent where all of, oh, it's so confusing. So confusing. If the XOR state is non-zero, then you're in a winning. You have a winning strategy, right? You're in a winning state, and that means that all of the states that you're going to move in, that you can transition to, are losing states for the opponent, right? And there's it means that all of those are losing states for the opponent, which is a little confusing because winning and losing can be defined with someone's perspective in mind, right? I think that's why it's a little confusing. How do they describe it? So All game states are either winning or losing. Winning are those which there is a move that causes the inevitable defeat of the player, even with their best response. So the other player is looking at a losing state. Losing states are those from which all moves lead to winning states for the other player. Whereas, yeah, so there's like some symmetry there, where every winning state for player A is a losing state for player B, and vice versa. Every winning state for B is a losing state for A. So that's kind of the key. That's like a really important part of this. And it's a little confusing, as I said. But yeah, that's like the basis, I guess. One important thing. And then, so if you we could just read the proof and try to understand it. Well, I want to say, like, I should be able to prove it without actually reading this. Like, that's kind of what I want to, like, challenge myself. Like, I should be able to do that in theory. Like, it's not too complicated. It's a relatively simple proof, I believe. So the key is seeing this XOR sum, right? So if you notice that this XOR sum is 0, then of all the states, of all the piles, if that XOR sum is 0, then you're in a losing state. And if that XOR sum is non-zero, then you're in a winning state. You notice that that seems to be true. Let's see if we can prove that that's true. So let's do it by induction. We're going to say, suppose that that is true for all the states that you can reach from the state that you're in, right? It's inductively true. So all the other states, if their XOR sums are 0, then those are losing states. Now those are losing states for the player's perspective that you were looking at. See, that's the tricky thing too. From player A, when you move, they are now looking for the perspective of player B. So whichever player's perspective it is at that point, it's going to be the losing state for that player if that XOR sum is 0, and it's going to be a winning state for the other player if that XOR state is non-zero. Excuse me, it's a winning state for the player's perspective from the new player's perspective, second player's, let's say the other player's perspective. It's a winning state if it's non-zero, it's a losing state if it's 0. And vice versa, any moves from those positions. Switch to the other player's perspective and it'll be, if you're looking at it, if that player's looking at a 0, it's a losing state. If they're looking at a non-zero, it's a winning state. Okay. Extremely, I think, it's okay. It's okay. We could express it that way. That's fine. That works. So that's the inductive argument, right? Now, let's say we're player A, and so we want to prove that this is true, starting from player A's perspective. And again, this is a symmetric, right? There's a symmetric argument for player B, but we start from player A, and we say, all right, for any move that we make from A, there are a number of them, basically some decrement in any particular pile that exists, gives us these different series of states. And what we want to say is, so we have two cases, right? We could be looking at 0, where we want to say that this is, in that case, if the XOR is 0, then we're in a losing state. And if it's non-zero, then we're in a winning state. So for player A. And actually, we don't really need to prove it for B, because if we prove it for A, then the symmetric argument holds already, so you don't really need to look at the other perspective for B. So let's just look at A and B, A to B. So in order for A to be in a winning position, so let's say it's non-zero, right? In order for A to be, we're starting at non-zero. In order for A to be in a winning position, what does it mean to be a winning position? A winning position is when all of the other positions that you can go to are losing positions for the other player, for player B. So that means if they're losing positions for player B, that means all those positions are going to be an XOR sum of 0. So that means that player A, no matter what, no, excuse me, there's at least one position that player A can go to where player B is losing, right? So that means that there's some way we can XOR, we can modify our non-zero XOR and get it to 0. That's pretty much what that means from player A's perspective. And then player B is looking at a losing position, and then so that means that player A can win. So player A only has to have one position that's a losing position for player B, or one winning position for player A that it can transition into to make the player A's position a winning position. So how can we do that? Is there always at least some move that can be made? Now again, you can only pick one pile and modify it. So if the XOR is non-zero, and you want to make it 0, how can you do that? How do you make an XOR go from non-zero to 0 in all cases? Well, there's one if there's one here if they start with S is 0, but so let S not be equal to 0. Okay, so this is actually the one that we're interested in. Consider the binary representation of the number S. Let D be the number of its. So okay, so I actually don't know the answer to that. Like my thinking is like, well, you've got a bunch of piles of numbers, right? And somehow you want to get to 0, the XOR. And they're saying, think about the binary representation. Well, let's not think about the binary representation for just a moment. Let's think about let's think of some examples, right? Let's not do that just yet. Let's think of like some examples that maybe we can use. So like let's say like 1 3 3, right? This is XOR of 1. We can go to 1 0 3 3, right? That gives us an XOR of 0. How about like 3 3 3? We can go to 0 3 3. How about like 1 3 5? How do we get 1 3 5 to be an XOR of 0, right? And the suggestion was look at the bits, right? So 5 has 1 0 1, 3 has 0 1 1, and 1 has 0 0 1. So my thinking here is like, oh, actually that makes sense. Yeah, you can. Okay, that actually makes a lot of sense if you consider the bits. Yeah, I mean there really is no other way to think about this other than to consider the bits, because if you XOR these numbers, like how are you supposed to know what you need to add or remove in order to cause these all to become 0? So like this is really interesting. This is super interesting because it's really not obvious, but once you see it, it's like kind of obviously true. So actually the answer is kind of straightforward. So you could take the largest number, right, and you can remove as much as you want from that pile in order to flip the bits, all the bits any which way you need. So anywhere you see for the rest of the it's actually kind of easy to explain then, kind of easy to see and understand. So yeah, okay, so you can always get this to 0. So what you would say is, okay, take all the bits that have a parity of so you're gonna take all the bits that have, after you've XOR'd everything else except for the largest number, you're gonna have a sequence of 0s and 1s, right? All the bits that have 0s, you want the largest number to have 0s in those positions. Actually, forget that. Basically, if you XOR all the other numbers and you get 0s and 1s, you want to take the largest number. I think you could say necessarily those though that number, the resulting number is necessarily smaller, less than or equal to the largest number. You want to take the largest number and make it equal to that number, and so you just take the difference between those. That's the move you make. So in this case, if you XOR 3 and 1, you get 0, 1, 0. So you want 5 to go to 0, 1, 0. So the difference is going to be, that's actually 2. 5 minus 2 is 3. So you're going to take 5 minus 3 and go to 2. And so now if you have 1, 3, 2, the XOR of 1, 3, 2 is 0, 1, 0, 0, 1, 1, 0, 0, 1, which is 0. Which is which is exactly what you're looking for. So yeah, okay, great. So if you're in a winning position, you can always go to a losing position for the other player, which is just the other player goes to s equals 0. Now the other part of it is that if you're in a losing position, you can always go to a winning position. You can always go to a non-zero position. So if you're in a losing position, that means if you're looking at 0, 0, 0, now this gets a little tricky. If you don't have any states to, assuming that you have moves to go to, yeah, I guess both of these are assuming that your piles are non-empty, right? Assuming that you have moves that you can make at all. So let's say somehow your all of your bits, you have 1, 3, 5 again, let's say, and let's say it's actually, well, we can go 1, 3, 2. Let's try that. Let's go to 1, 3, 2. So now we're in 1, 3, 2. Also, I realize these are kind of backwards, right? It's probably more like 0, 0, 1, 0, 1, 1, 0, 1, 0, but whatever. So now if we think about okay, we have 1, 3, 2, we're in a losing position. I want to show that from this losing position we can always move the other player. We can only move the other player into a winning position. In other words, only moves you can make from this position gives you an XOR sum that's non-zero, right? So all of the transitions you can make. So that's kind of interesting. Well, basically, if you consider the XOR of the entire thing, any single bit that you move, that you change, you modify, obviously is going to give you an XOR that's non-zero. So any power of 2 that you change that you make. But what if you change multiple bits at the same time? Well, since you're only modifying one number at a time, whatever amount you remove, you can kind of take the inverse, I guess we'll call it, where there's some difference k, but the result ends up being some number of bits flipped in the some number of bits flipped from 0 to 1 or 1 to 0. Yeah, some number of bits being flipped on the number that you're modifying, any number of bits, more than one, and because you're only modifying that one number, it's actually the best way to explain it is, if you any change that you make on any pile is going to, if you look at the bitwise, is going to modify every bit, but any particular bit, any number of bits, it's going to modify the parity of that bit, and it's going to flip that bit from, it's going to modify the parity of that bit from 0 to 1. and you can't escape modifying at least one bit to 1. Right? Any change is going to have at least one of those bits flipped. Some change will have more than one bit. It's the parity. It's not just the parity. It's the number of bits in the XOR sum, which gives you the it's like modulo 2. The number of bits modulo 2 will flip from 0 to 1, no matter what change you make for that particular number, because the change you make in that particular number is only going to change the So okay, you can think of it this way. Let's take any particular bit and count the number of bits present in the XOR in all of the piles, right? That gives you a particular sum of bits. In the XOR sum, we know that that's even, right? Oh, hello. Hello, IRCA, welcome. Hello. Hope your day's going well. Welcome. Yeah, so we can do it this way. We can say, praise God. Praise God. Yeah. Or just praise God in general. I don't know. I don't know if that's blasphemous, but just kind of like casually say that, you know? I don't know. Maybe I should do that. But welcome. So you do it this way. Consider so your XOR sum is 0. That means that for every bit position, the number of those bits that are 1 in all of the piles that you have must be an even number, right? Because when you XOR those even numbers, they become 0. You basically take the modulo 2. And then in order for the XOR sum to be 0, all of those bit positions have to be 0. So for any given bit position, we know that the total number of bits across all the numbers is even. If you make any kind of move on one pile, then you're going to affect at least one bit, but it's true for all of the bits that you modify. So you're going to modify a non-zero number of bit positions. Forgive me, you're going to hear a small buzzing noise because I'm charging the headset now. You're going to have a non-zero number of these bit positions. You're going to modify them, and because you're only modifying this one number, you're necessarily either increasing or decreasing so let's take one bit position that's going to be modified. Necessarily increasing or decreasing the number of bits in that bit position by 1, which means you're going from an odd number of bits to an even number of bits, which means that bit position will be set to a 1 in the XOR sum at the end. And if any of the bits in the XOR sum are set to 1, then the XOR sum is no longer 0. So any change you make is going to put you back into a non-zero XOR position. That's all you need. That's it. Those two proofs. That shows that if you're in a non-zero position, there is a move you can make to get to a 0 position, and if you're in a 0 position, then any move you make is going to put you in a non-zero position. And that's probably exactly what they have here. So let's see this. So their explanation. So we'll read their explanation for if you're. Let's say if you're starting in a 0 position, then any move you make, right, is going to flip one of the bits, basically, or it's going to flip one of the bits and cause your even bit position to become odd, which makes it no longer an XOR sum. It makes it a non-zero XOR sum. So consider any move. This move reduces the size of a pile X to size Y using elementary properties of XOR. We have T equals S XOR X XOR Y, where S is 0, right? Which equals 0 X or X XOR Y. So you reduce the pile X to Y, S XOR X XOR Y. I don't really understand this. T is prove there's a move leading to a state with T equals 0. I want to show that T is not 0, but why is T X S XOR X XOR Y? Oh, I think I understand, because when you take S and you XOR X, it removes X, and then you XOR with Y and it adds X. Okay, that's really interesting. I didn't think about doing it that way. So now you have T equals X XOR Y. But we know that X is not equal to X, Y, so this is non-zero, right? Since Y is less than X, this can't be 0, so T is not equal to 0. All right, that's like that's an algebraic way of doing it. I did it like a bitwise kind of argument, but this is a lot cleaner. Means any reachable state is a winning one by the assumption of induction, so we are in a losing position. Yeah, I think specifying what the what do they call that? Well, I guess you don't have to specify the perspective. For me, it's like a lot easier to understand if I specify the perspective. So any reachable state is any reachable state from S is 0 is non-zero, and we said non-zero is a winning state for that player's perspective. So any reachable state is a winning one, and that means that we're in a losing position, right? So, right, this is by induction, they're winning. And then now we suppose if we're not 0, then we can take the largest value, largest number, D be the number of its leading non-zero bit binary representation. Yeah, so if you consider the binary representation, what you can do is take the largest number and then take the XOR of everything else except that largest number, and the move you want to make is going to transform this largest pile into the XOR of everything excluding that largest pile. And then what that means is that these two values are equal. The XOR of everything else and this pile are now equal, and they take the XOR of that, and it's 0. And basically, yeah. So that's kind of what they say here. So you're going to say there's a move from X to Y, and we want to make Y the the XOR of everything excluding X. So this is from X to Y. You take the XOR of X. Now X is gone out of S. XOR with Y. So this is going to be basically, this is going to be equivalent value to removing X and then adding Y, or removing part of that pile. And then what you want is Y to be S XOR X, which if as long as you take X to be the largest pile, then you should always be able to calculate. Then S XOR X will always be less than X. So then you should always be able to transition from X to Y. We can define Y to be S XOR X, which is exactly that. Yeah, okay, that's interesting. Super interesting. And then that becomes 0. Wow. Let D be the number of its leading biggest value non-zero bit. D be the number of its leading non-zero bit. Consider the binary representation of S, number of S. D be the number of its leading non-zero bit. Move will be on a pile whose size's bit number D is set. It must exist, otherwise the bit wouldn't be set in S. We will reduce its size X to Y equals X XOR S. All bits at positions greater than D in X and Y match, and bit D is set in X but not set in Y. Therefore Y is less than X, which is all we need for a move to be legal. Now we have. Okay. You don't necessarily need to take the biggest number though. Right, they're saying, actually it might not be correct, actually just take the biggest number. I was thinking the biggest number is what you want, but the truth is the two biggest numbers could cancel out in the XOR, I guess. It doesn't really matter, actually. It doesn't really matter. You could just take any number that has the largest bit set in it, which also could be, which is a kind of necessarily the largest number would have that bit set. Otherwise, it wouldn't be the largest number, right? If that bit's not set in that largest number, then the number where the bit set is necessarily larger than the largest number, so it can't be the largest. So both works. but it doesn't have to be the largest. You just have to be any pile where the largest bit in S is set. Must exist, otherwise the bit wouldn't be set in S. And right, reduce its size. Now, does it have to be the largest bit in S? It could be any bit. It doesn't matter. Like as long as this is 0 at the end. As long as the number you're working with is larger than X XOR S. That's really the key. Which maybe it's not. Maybe it's not true. I'm just thinking. Actually, this could be incorrect what they have here. This might be a wrong proof. The example I'm thinking of is 10011 1001 0010. So you could do 1011, right? If you do something like this, the largest bit that's set in S, and S is not 0, is 00100. If you select if you try to, well, actually, I don't know. Could do 0. I don't know. Maybe I'm wrong. Oops. No, never. No, it's fine. It doesn't matter. No, it doesn't matter. I take it back. It doesn't matter. You could do either one. Either one works. You could use the largest number, or you could. It doesn't matter which number you use. You could use the largest number, but it actually doesn't have to be the largest. It just has to be big enough to be bigger than any of the bits in S. It just needs to be larger than S. That's what it comes down to. And yeah, just be able to contain all the bits in S. Because basically, you're going to take all the bits in S, you're going to flip them, and flip them. So as long as you're at least as large as now, no, you could have a position where you have this, you have like a 1 here, but if you pick this bit, you might end up here, and then S is not larger than X XOR X. No, it is though. No, it always is. Yeah, because if you remove this bit, if you XOR this and get rid of this bit, then S is always larger. Okay, never mind. No, we're fine. It's a little confusing, but okay. This is like a slightly more refined approach what they have here. I think the largest number works too. Largest number works too in the set, but I think it's easier if you just pick any number that contains the largest bit from S, the most significant bit, non-zero bit. Then you can reduce to Y equals X XOR S, and then you can get 0. All bits at positions greater than D and X and Y match. All bits at positions greater than D in X and Y match. Okay, wait. Why do they prove? How do they prove that Y is less than X? So all we need for remove to be legal. Okay. So all bits at positions greater than D in X and Y match. I think that's true because we said find the leading non-zero bit in S and find a pile where that bit is, that's a D, let that be D. Find a pile where D is set, which it must exist, and then consider X and Y where Y is X XOR S. Okay. Now The suggestion is all bits at positions greater than D and X and Y match. Right, and the reason they match is because the leading bit for S is set to 1. All the bits to the left, that's D, all the bits to the left, that's the leading bit for S. So whatever is in X to the left of D is untouched by this XOR with S. Basically XOR with 0 for all those bits. That's another way of expressing that. So these are all the same after you take the XOR with S. And bit D is set in X but not set in Y. However, yeah, so everything greater than D is the same. However, bit D is set in X necessarily, but it's not going to be set in Y because X and S both have bits set to 1 at D. So D is 0, but all the bits. So if you take the XOR of, well, yeah. So this bit is set in X but not set in Y. Okay, got it. Therefore, Y. Oh, I see. That's why they're trying to explain that. That's why they could say that Y is less than X. So all the bits greater than D are the same. However, D itself, because it's set in X and it's set in S, we know that D is 0 in Y, but it's set in X, which means that X is greater than Y, which means that this is a legal move. Okay, got it. Fair enough. And then from there, you can make this move, and you'll get 0. All right. Okay. Not exactly how I would have explained it. Not the approach I took. The approach I took still works, I think. Yeah, if you just take the largest number, you can show that the XOR of the entire set is always going to be smaller. Excuse me, take the largest number and take the XOR of the set without that largest number, and the XOR of the set without that largest number is always got to be, at least it's got to be smaller than that number. And is that necessarily true? Actually, what I suggested might not even be true. Just thinking here. No, I don't think what I said is even true. No. Well, grateful that they proved this here, but what I said was wrong. If you take the largest number, call it, we'll call it Q, and you say S XOR Q. We want to prove that that's smaller than Q. So that way what we can do is remove Q and then XOR S XOR Q, which gives you S XOR Q XOR S XOR Q, which is 0. But is it, if Q is the largest number in the set in the pile, the XOR is S XOR Q smaller than Q? Excuse me. I think it is necessarily, because Q is non-zero, right? Because it's the largest value. And no, I mean, I don't know, actually. Am I thinking, how do you prove that it's smaller? We have a bunch of bits flipped for S, and then since Q is non-zero, you might actually flip bits on for S. Well, since Q is the largest, it has the leading bit of all of the other bits. But maybe, yeah, actually I'm wrong. I think I'm wrong. I think you need to take the, yeah, I think you need to take you need to take the. It's not necessarily the case that the largest number would have the leading bit of S in it, right? Because the leading bit for S could actually, the leading bit for S could be basically, yeah, you could be in a position where S XOR Q is larger than Q, even though Q is the largest number in the set. Because the leading bit for S could be smaller than the leading bit for Q. And then that means S XOR Q makes that leading bit for S flip positive. And you could imagine, I mean, you could imagine Q being just one bit, 1 power of 2, and then S is a smaller power of 2. And then when you take S XOR Q, even though yeah, so I mean, you can actually show this, right? You could do 1 0 0 0 1 0, and then S at the end. So S is 0 1 0, Q is 1 0 0, and this XOR is definitely larger than Q. How do you get S to be 0 1 0? You could have some other number that cancels out Q. And yeah, and then actually that could be, so you could have 4 2 4, and then that gives you the XOR of 2. And then if you pick 4 and you try to XOR that with S, you get 1 1 0, which you can't actually make that move because 4 is too big. So you would actually need to pick 2. You can't move 4 to 6. Which is kind of interesting. You want to go from Q to S XOR Q. But if you pick 0 1 0, that, which is 2, you can go from, really it's 2 to 0. S XOR X, in this case X is 2, is actually 0, right? X is 2, S is 2. So yeah, so I'm wrong. I'm actually just wrong. Okay, it's a good thing we proved that. I'm a little disappointed. Thought I had that. Thought that would work, but this logic makes sense. So all right, it's a good thing. It's a good thing we're looking at studying it. Correlate. Any state of NIM can be replaced by an equivalent state as long as the XOR sum doesn't change. Moreover, when analyzing a NIM with several piles, we can replace it with a single pile of size S. Oh, that's so interesting. Okay, cool. So, yeah, you only care about the whether or not this XOR sum is 0 or not. So, so if you have several piles, you can just plop it into a single pile of size S, where S is either 0 or non-zero. Any state of NIM can be replaced by an equivalent state as long as the XOR sum doesn't change. Oh, interesting. You need the XOR sum to be the same though, so size S. Right. Okay. Cool. So every state could basically have its own integer. That's really interesting. The equivalence of impartial games in NIM, Sprague-Grundy theorem. Now we will learn how to find for any game state of any impartial game a corresponding state of NIM. Lemma about NIM with increases. Okay, so now we're going to extend this to other games that are impartial, two-player, perfect information, finite impartial, perfect information, two-player games, in which winning and losing depends on the state of the game. The only difference between the two players. Well, that's impartial, I think. Yeah, that's what this part means. Okay. Excuse me. Wow, that's super interesting. Okay, so this corollary, that's pretty significant corollary, right? We can replace any state of the game with a single number, which is the XOR sum. And so we can really just consider these to be single piles with that size S. Awesome, we get the same analysis for winning and losing. Okay. So that tells us whether or not we're in a winning or losing state very efficiently, very quickly. We have equivalent states for a single number. It gives us an equivalent state. The equivalence of impartial games in NIM, Sprague-Grundy theorem. Now we will learn how to find for any game state of any impartial game a corresponding state of NIM. Lemma about NIM with increases. We consider the following modification to NIM. We also allow adding stones to a chosen pile. The exact rules about how and when increasing is allowed do not interest us. So we don't actually care how and when you can add stones. However, the rules should keep our game acyclic. In later sections, example games are considered. Okay, so it looks like we can kind of modify whether or not we can add or remove stones. We just need to make sure that we can't. Okay, well, now here's the thing. As long as you can remove stones, I think you're okay. But they're saying if you can add stones, as long as you can't go back to a state that you're already in. So you just need to make sure any adding that you do keeps the game acyclic. Later sections example games are considered. All right, so I'm not totally certain, don't fully understand, but we'll keep that in mind. The addition of increasing to NIM doesn't change how winning and losing states are determined. In other words, increases are useless and we don't have to use them in a winning strategy. Proof. Suppose a player added stones to a pile. Then his opponent can simply undo his move, decrease the number back to the previous value. Since the game is acyclic, sooner or later the current player won't be able to use an increase move and he'll have to do the usual NIM move. Okay, that's really confusing, but I guess basically the rules do matter. If you can always decrease after the increase, then I guess as long as the increase doesn't make the game cycle somehow. Acyclic, I think, referring to the states you can go to from a particular state. So it's a little confusing because if the player is in a losing position and they increase the stones, it doesn't matter if it's a winning or losing position though. Whatever position they're in, the other player could just move back. So, all right. And then they're both in the same position they were in. Okay, that's really interesting. Yeah, the state doesn't really change. The state of the game doesn't really change if they just keep moving back and forth like that. I'm wondering, but you have to have this idea that you can always remove stones as you wish. right? Like if they're, and how can you add stones to make the game cyclic though? I don't know if there's a way to do that. I think if we suppose that it's, well, it's always acyclic, the game, right? So whatever, yeah, so whatever rules, that changes that are made, we need to just make sure the game is still acyclic, and you still have this ability to make the moves to determine the winning and losing states. I don't know if there's a way to change the rules about adding stones in such a way that that the game is not acyclic anymore. I don't know. I'm actually not really sure about this part, what this means, like if there's even a way to do that. But since it's acyclic, sooner or later you won't be able to. Oh, I see. I think I get it. In other words, you can't just add stones infinitely over and over again, where the player removes the stones to bring you back to undo that move. You can't do it infinitely, such that the game is infinite. It's not a finite game anymore. Also, I'm not sure this is looking at me. Yes, okay. Yeah, I think I get it. Okay, I understand. So, yeah, okay. So you basically have to have rules for adding stones in such a way that the game will still end even though you're adding stones. And even if you just keep adding stones and the player undoes the adding, and they add them again, they undo it, and add it, undo it. Even if that happens, the game, eventually has to end. So the player eventually has to do a move that's not an adding move. Okay. That's interesting. Okay, yeah, because if you could just always add stones whenever you want, however you want, then that very quickly becomes cyclical, right? So the game has to be necessarily acyclic. Sprog Grundy, okay. Let's consider a state V of a two-player impartial game, and V sub I be the states reachable from it. So let's consider state V of a two-player impartial game, and let V sub I be the states reachable from it, where I is an element of 1 to k is greater than or equal to 0. So, okay, so you can reach V sub I from V. To this state, we can assign a fully equivalent game of nim with one pile of size x. So V has a size x. The number x is called the Grundy value or nim value of state V. Alright, so there's some XOR sum we can give V, and we don't know what that is, we'll call it x. Moreover, this number can be found in the following recursive way. X is the mex of all of the other state values, where x sub I is the Grundy value for state V sub I, and the function mex, minimum excluded, is the smallest non-negative integer not found in the given set. Okay, so if you take all of the states that you can go to, those all have Grundy values. This Grundy value at the state you're in can be defined recursively by saying take the minimum excludant of all those values, the set of all those values, which is the smallest non-negative integer, which I think is not 0 also. I don't know if it's 0 or non-zero, it includes 0 or non-zero. Not found in the given set. I think it can be 0, the value that's not there. That's what x is going to be. So if all the other values are positive or non-zero, then x has got to be 0 because you're moving from 0 to non-zero, right? All the other ones have to be 0. If any of the other ones are 0, then this one is not 0, right? It's basically the deal with the Grundy values, and I think the excludant makes it simple, so that way in every case, so that encapsulates that property where the winning states or the losing states are 0, and the winning states are non-zero, and also it makes sure that all of the state values are unique, right? Viewing the game as a graph, we can gradually calculate the Grundy values starting from vertices without outgoing edges. Grundy value being equal to 0 means a state is losing, right? So if you don't have any outgoing edges, so you can go sort of bottom up, I guess, if you wanted to, or you can do sort of a top-down recursive thing. But yeah, really the base case is the ones that don't have outgoing edges, and those will all be 0. That's super interesting. It's really interesting. Wow. So if you're in a state where all of the other values are 0, all of non-outgoing edges are 0, then your state is a 1. Your state is not losing. And then if you have another state where like all the states are 1, 2, and 3, and then your state now gets a 4, and that's not losing either. Oh, no, well, you do 0, 1, 2, and 3, and then now your state is 4 is not losing. Yeah, that's really interesting. So that's where this mix comes from. It comes from the fact that you could a losing state is 0, a non-losing state is a winning state is non-zero, and for a losing state to be a losing state, all of its outgoing transition states, all of that, in order to be 0, all of them have to be non-zero, which is the mex, right? All of them being non-zero means 0. That's the first one that's excluded. And then for a state to be non-zero, all of its excluding has to have at least one that's a 0, right? If at least one is a 0, then it doesn't matter what all the other ones are. At some point, you're going to have either 1 or a greater number. And using the minimum excludant also allows you, it gives you that property, and it also gives you sort of uniqueness, I guess, as you traverse, as you go further up, as you assign numbers to your graph. But I think realistically, you don't actually need to. You could just assign a 1 or a 0. I think it might be more efficient to assign a 1 or a 0. I'm not sure if it really matters, because if you assign a 1, then yeah, I'm not really sure it matters, because I think in every case you end up having to look at all of the outgoing edges for that node anyway. You just have to do the graph. You have to visit every node once anyway. Yeah. Visit every node at least once. Yeah, you have to visit every edge at least once. Yeah. So you always end up with so actually it doesn't really matter what numbers you assign. Because you're going to add all these things to the set anyway, and then when you go through the set, you might be like quote unquote doubling the work, but asymptotically that doesn't really matter. You're going to have to visit every edge at least once, no matter what you do, and the edge set's quadratic with respect to the number of points. So the number of states in the game, you have to do O of let's say s squared, where s is the number of states, because that's the edge set. The edge set's quadratic in the worst case. It's acyclic, so it's probably not too bad. But kind of interesting here. I don't know. I don't know if this mex is entirely necessary to do all the like the integers, assign them that way. I think you can just pick 0 or 1, really. Viewing the game as a graph, we can gradually calculate the Grundy values starting from vertices without outgoing edges. Grundy values being equal to 0 means the state is losing. Use a proof by induction for vertices without a move. Value x is the mex of an empty set, which is 0. That is correct since an empty nim is losing. Now consider any vertex v. By induction, we assume that the values x sub I correspond to its reachable vertices are already calculated. Let p be the mex. This we know. Then we know that for any integer I element of 0 to p excluding p, there exists a reachable vertex of the Grundy value I. This means v is equivalent to a stated game of nim with increases with one pile of size p. In such a game, we have transitions to piles of every size smaller than p, and possibly transitions to piles with sizes greater than p. Therefore, p is indeed the desired Grundy value for the currently considered state. Oh. Interesting. Oh, okay, I guess there's some increases too. Right, I didn't really think about that you could have increases or decreases. That might be why. Oh, I see. Okay, that's why you want to use the mex, is because you want this to, what's the word? You want this to match the nim games. Well, I was thinking about, like, you know, if your nim is, really only care if it's, no, I take it back. Okay, I'm wrong. I went too far. So you want to still use the XOR value, the nimber, I guess they call it a nimber, for a pile of particular size. You don't actually want to be looking at yeah, you want to have an analog between an impartial game and nim. You want to draw an analog between an impartial game and nim. So you don't want to immediately jump to 0 and non-zero states, right? In theory, you might be able to reduce the analogy, but for now, you just want to prove that this analogy works in the first place. I think what you can prove is that if this analogy works, then you can also use a mex that's just a 0 or 1, either 0 or non-zero or 0 or 1. What's the word? Assignment for the values, and you'll get the same, sort of true or false result. But actually, if you want to sort of quote unquote maintain the nimbers, I guess, I think you probably want to do it this way then. Okay. For vertices without a move, value x is the mex of an empty set, which is 0. That's correct since an empty nim is losing. Okay, got it. Can I consider any other vertex v? By induction, we assume the values x sub I corresponding to its reachable vertices are already calculated. Let p equals this mex. Then we know that for any integer I from 0 to p excluding p, including 0, there exists a reachable vertex. For any of these integers, there exists a reachable vertex with Grundy value I. Right, assuming that p is non-zero. P could be 0, right? If p is 0, then none of these values of I, yeah, but assuming p is non-zero. So there's some reachable vertex of this Grundy value I. Okay, got it, true. This means v is equivalent to a state of the game of nim with increases with one pile of size p. Okay, interesting. So yeah, and okay, I see. Oh, that makes sense. So because you can reach all these other states that are smaller than p, this is the same thing as a nim Number of P, I see. Equivalent to a state of the game of nim with increases with one pile of size P, because you can decrement any amount to get to any of the other states. And because there are numbers that are larger than P, you have some degree of increases that also you from the state you can go to the increases rather. In such a game, we have transitions to piles of every size smaller than P, and possibly transitions to piles with sizes greater than P. Therefore, P is indeed the desired Grundy value for the currently considered state. I see. That's why you want to have this max value of decreases, because you want to draw an analog between nim and any impartial game. Okay, and you can define the Grundy value for any particular state of an impartial game. And so now basically, yeah, there's this analogous nim game using this recursive function. That's so interesting. Okay, so both of these things are like, I mean, all of these things are like pretty. I mean, they're all there. I mean, it's visible, I guess. It's knowable. But like all this is pretty hard to come up with on your own, right? Like it'd be pretty challenging to figure this out all on your own. Pretty amazing. But yeah, I don't know, man. Something about like appreciating God and the order that He's made in this world. You know, it's like it's pretty astounding when you kind of discover these different pieces, different things. So yeah, pretty amazing. Okay, application of the theorem. Finally, we describe an algorithm to determine the win-loss outcome of a game. Finally, we describe an algorithm to determine the win-loss outcome of a game, which is applicable to any impartial two-player game. Finally, we describe an algorithm to determine the win-loss outcome of a game, which is applicable to any impartial two-player game. To calculate the Grundy value of a given state, you need to get all possible transitions from this state. Each transition can lead to a sum of independent games, one game in the degenerate case. Calculate the Grundy value for each independent game and XOR sum them. Of course, XOR does nothing if there is just one game. After we calculated Grundy values for each transition, we find the state's value as the mex of these numbers. If the value is 0, then the current state is losing, otherwise it is winning. In comparison to the previous section, we take into account the fact that there can be transitions to combined games. We consider them a nim with pile sizes equal to the independent game's Grundy values. We can XOR sum them just like usual nim according to Booton's theorem. Excuse me. Okay. Yeah, so you can XOR combined games. Just slap them together. Because every it's like a new game is like a new bunch of piles, and then those piles are basically could be a single pile, and then all those piles put together is basically just XOR. Okay, that makes sense. So so calculate the Grundy value of a given state. You need to get all possible transitions from this state. Each transition can lead to a sum of independent games, one game in the degenerate case. Calculate the Grundy value for each independent game and XOR sum them. Of course, XOR does nothing if there is just one game. Okay, I think I understand. So the transition can be a sum of independent games. Yeah, this is like pretty special piece here, but it depends on the game. But the transition could be like, so in nim, the transition is basically you just assign the set of piles one number, and then you have a transition to all of the smaller piles, I guess. I think what's being suggested here, though, is that a sum of independent games would be like So each transition, so the transition itself, that could be, instead of one game, it could be a sequence of a bunch of games, I guess, independent games, and then in order to get the Grundy value, you want to calculate the Grundy value for each of those, and then take the sum, the XOR sum. So that, I don't think I fully understand. I think I get it actually. This is due to Booton's formula again, because like basically what you transition to, it's not just one game, it's a set of independent games. Right, I've actually seen that before, how that could happen. So calculating the Grundy value for that particular transition state would then actually becomes calculating Grundy values for each of the independent games, and they have to take the XOR of those to get the Grundy value for that state transition, total state transition. And you do it recursively, right? Same deal. Each of those games now become their own game that those could has its own transition states. So this is kind of a special acyclic graph, I guess. Becomes a special acyclic graph. Just depending on how you transition, you could end up with multiple independent games, which is not obvious how that happens. I don't actually have enough experience to know, like, well, what does that end up looking like, and in sort of in some certain concrete cases, and then in the general case. And then after we calculated Grundy values for each transition, we find the state's values the max of these numbers. If the value is 0, then the current state is losing, otherwise it's winning. Comparison to the previous section, we take into account the fact that there can be transitions to combined games. So this is this is the combined game. These are the combined games, transitions to combined games. We consider them a nim with pile sizes equal to the independent game's Grundy values. We can XOR sum them just like usual nim according to Booton's theorem. Okay. Patterns and Grundy values. Very often when solving specific tasks using Grundy values, it may be beneficial to study the table of values and search for patterns. In many games, which may seem rather difficult for theoretical analysis, the Grundy values turn out to be periodic or of an easily understandable form. In the overwhelming majority of cases, the observed pattern turns out to be true and can be proved by induction if desired. However, Grundy values are far from always containing such regularities, and even for some very simple games, the problem asking if those regularities exist is still open, e.g. Grundy's game. So, basically, computing Grundy values may or may not be that easy. Interesting. Overwhelming majority of cases, you can find a pattern for the Grundy values. However, Grundy values are far from always containing such regularities, and even for some very simple games. The problem is open, asking, do these regularities exist? Still an open problem. That's very interesting. Okay. Now we have some examples of what we can use. Oh, we have one example game. Okay. Crosses. Okay. Consider a checkered strip of a size 1 by n. In one move, the player must put one cross, but is forbidden to put two crosses next to each other in adjacent cells. As usual, the player without a valid move loses. Okay. So let's think about it ourselves first before we look at the answer. I mean, I kind of already looked at the answer, but super simple game. All right. So we want to calculate the Grundy values of this game, right? And this is an impartial, finite. What do you call it? It's an impartial game. It's a Yeah, an impartial two-player game. Okay. So this is an impartial two-player game, right? We have all full information. It's finite, right? Player is going to lose. There's two players. Every player has the same moves. It just depends on the state where you can move. And what else do we need? Yeah, perfect information, finite, impartial, and that's it. That's actually it, I think. Impartial, perfect, and information, and two-player, impartial, perfect information, finite. Yeah. So it's equivalent to nim. Or you can draw an equivalence to nim. Now, the game that we're looking at actually in our Leetcode problem is perfect information, two-player, impartial, finite. Yeah, so you can apply Sprague-Grundy. That's what we're going to do. So let's say, okay, 1 by n, right? We said two-player, perfect information, finite, and impartial. Impartial means that yeah, the moves don't matter based on the player. Like either player, it depends only on the state and the player who's moving at that time. Yeah, okay. So yeah, it's impartial, two-player, finite, and perfect information. So consider a checkered strip of size 1 by n and one move. The player must put one cross, but it is forbidden to put two crosses next. As usual, the player without a valid move loses. Forbidden to put two crosses next to each other in adjacent cells. So, not sure what we're trying to figure out here. I guess we're trying to figure out is who's the winner. Something like that. If our initial state is winning or losing for the first player, I guess. So we want to take the max of all the possible moves, so our cross can be put in any position, and the edges left and right gives us sub games of gives us an independent game, or yeah, gives us a sub game that doesn't include that. Actually, we lose two what do you call that? Two positions, right? On the left, two positions on the left side, two positions on the right side, which is effectively the same game, but twice. So on the edges, you have those games happen twice, and each of those transitions. That's really just the same transition, I guess. And then you have any other move for the cross. What you're transitioning to is an independent game on the left, an independent game on the right. The left side, you are actually the first position, you're losing two spots. Second position, losing 3 spots. But the third position, that's when you have independent games, right? The left and right positions disappear, and so you have a game. So I guess if you have some particular I, and I is going to be from, it's going to be 0, 1, 2. For I is from 2 to n. It's got to be there's position n minus 1, n minus 2, n minus 3. So 2 to n minus 3. Any I in that inclusive range, you're going to end up with I minus 2. So 0 to I minus 2, index 0 to I minus 2 is the one independent game on the left side. On the right side is going to be I plus 2 to n minus 1 inclusive, that's going to be two independent games that you XOR the Grundy values of those two for that transition state. And so those are all of the transition states. Right, you don't need to do the edges twice. You can just do them once, right? They're gonna have the same value. So in those cases, it's single Grundy value, and then a whole bunch of Grundy values for these independent games. And then you take the mechs of all of those values, and that's how you compute the Grundy value recursively for this game. So that's what I say. So g of n minus 2, and then g of I minus 2. Oh, that's interesting. So right. So you only need the size of the strip. Right. You don't actually need from. Yeah. So actually, I minus 2 is fine to give you the size, and then n minus I minus 1 is the other portion. But the question here is, why is it and they explain that here. A player puts a cross on in a cell. We can think of the strip being split into two independent parts, to the left of the cross and to the right of it. In this case, the cell with a cross, as well as its left and right neighbors, are destroyed. Nothing more can be put in them. Therefore, if we number the cells from 1 to n, then putting the cross in position I less than n breaks the strip into two strips of length I minus 2 and n minus I minus 1, i.e. we go to the sum of games I minus 2 and n minus I minus 1. For the edge case of the cross being marked on position 1 or n, we go to game n minus 2. So I think g of 0 though is, so that's like a kind of a subtle thing where I think there are multiple edge cases here, right? So if you, well, yeah, I mean, I guess you're fine. So n minus 2 makes sense when you put the cross on I equals 1. But what about now we're saying, yeah, but when you put it on I equals 2, then you're destroying actually 3. You're destroying the left and the right, and so n minus I minus 2 gives you n minus 3, and then I is 2. This is g of 0. I guess g of 0 is 0 by default. So then this is just, so then yeah, in that case you still get that sort of degenerate case here, that, or you still kind of get that degenerate case here, I guess. So this is a little bit different from how I would have defined it, but this ends up being the same thing actually, and because the strips are like, they're just 1 to n, right? You don't actually need the 2 coordinates to give you the strip. It could just be the size of the strip. So that's really interesting. So this ends up being quadratic time solution. G of n has a period of length 34, starting with n equals 52. And that's super interesting. So this ends up being, so this can be calculated in constant time, as long as you calculate the first 34 values. As long as you calculate the first 86 values, right? The first 52, and then the 34. That 34 period. I guess you just have to prove that 34 period exists. A period exists. So that's super interesting. Okay, so I think I get it. I think we're getting it. I think we understand it. Let's see if we can apply it to our problem. Let's see what we do. So I'm going to go ahead and save this. Yeah. This fails if we increase the load though. Yeah, TLEs. Let's see if it'll work for 25 though. want to save this. Yeah, Teely's at 25. Let's go to 21. Should be okay for 21. Let me go full screen for a moment here. Alrighty. Oh, yeah, it worked. It worked, but that tripled the time. Added one number, tripled the time. Alrighty, so let's save this. Okay. So I saved this as can I win 1 with underscores. And so yeah, so this is, it's pretty clear that this is going to be Sprague Grundy. Okay, now the question is, can we do this? How do we do this? We're gonna get to some total t, and we have some numbers. Call them x. So from one to x, and that the player can choose from. So the transition states are going to be oh man. Now this seems like it might be a little bit harder. Might be a little bit harder. So the transition states, initially you have t, and you have, t minus call it alpha, what you pick, right? And then alpha is an element of 1 to x. And then depending on what you picked, you can change the state. Just thinking here. I want to say something like you would have independent games. Once you pick alpha, then you have from 1 to alpha minus 1 is one game, and from alpha plus 1 to x is another game with t minus alpha and t minus alpha. I want to say something like that, and then you could XOR these two games. That's kind of what I want to say, and that somehow this t minus alpha is sort of imbued into the state of the game. Yeah. Yeah, you could redefine the game to be just consecutive values, right? Make the game with consecutive values and a particular total, and then these become subgames, and you could take the XOR of these independent subgames, which they are. I mean, they are just independent subgames at that point. Call it Grundy of S and T. It's going to be the mex of... Wow, that is ugly. Okay. So that's super awkward, this we got going on here, but pretty much we're going to use continuous arrays of values and make those subgames, and so we can take the XOR of those subgames for the Grundy values. And so we're going to say if we take the minimum of that consecutive sequence, then obviously it's kind of a degenerate case, so if we use the maximum, because we're not going to split into 2 different games. But if we use anything in the middle, then we'll split into 2 different games and take the XOR of those results. And the Grundy value is going to be the max of the union of all of those numbers. And we're also going to have this total passed around in each calculation. So that kind of gives us another dimension. So this kind of gives us something that's going to be it's going to be sort of not really dynamic programming so much, not necessarily, but O of the size of S. So each of these G values, this is O of S, this is O of T, right? More or less, and pretty much O of S times T, and then the mex itself, the number of numbers to calculate, number of times you calculate O of S, O of T is going to be O of S, so you end up with O of S, size of S squared T, which in our case we said T is 300 and S is 20, so this is like 20 squared times 300. So it should be relatively efficient. It should be quick, but still pretty inefficient for, like, as far as algorithms go, it's relatively inefficient. But this is definitely a lot faster than the than what I was going to do. The what do they call that? Is a lot faster than the brute force approach. The what do you call that? Is going to be a lot faster than the naive approach, or the exhaustive approach, I guess it's a better way of saying it. Yeah, the exhaustive approach. So yeah, pretty good. Let's see if we can code that. Let's see if we can do it. So we're going to have int b or a, int b. So this is an inclusive range from a to b of integers, and then also we're going to have a total. And initially we're going to calculate our range is going to be from 1 to max int, and our total is going to be the target here. And we're going to say we want the max, so I want to create this unordered set. Of integers, call this vals, calculate Grundy values recursively. There may be a better way to do this, by the way. I don't know. I think simplest thing to do is just dump all the values into a set. Base case. Excuse me. So if Oh yeah, what is the base case for our Grundy value? So you win if well, you're in a losing position if the Grundy value is 0. You have no outgoing edges. You have no more moves to make. That's if the total is less than or equal to 0, right? No, actually, you're winning in that position. Yeah, I want to say. It's two base cases. Well, it's just two base cases. Yeah, we'll say if B is larger than B is greater than or equal to total, turn true. Turn 0. In this case, so we say a winning state is, so that's a little confusing. When are you in a losing state? When are you in a winning state? Losing state means there's no outgoing edges, nowhere where to transition to. The losing state is, I want to say the losing state is when you're it's pretty much any time. It's a weird base case to be in. I'm trying to think about this. I'm also really hoping that this does have genuinely have an analog to the NIM game, and I can use Grundy Sprague. Sprague Grundy. Use Grundy theorem. That would be pretty upsetting if Grundy theorem didn't actually apply here. I was just wasting my time. True. Yeah. So true is non-zero. Or not equal to 0. Greater than 0. What? It doesn't really matter. The problem is, when do we return 0? When can the So actually, this is non-zero. These are sort of degenerate cases. When do we ever return 0, though? That's the problem. We need a base case that returns 0. When is that? There are no transitions to go to. Player has no moves. I want to say if the total is negative. That's pretty much, if the total is negative, then you've already lost. You can't make any moves. Yeah. That's what I want to say. I want to say that you lost at that point. That's probably it. That's probably it. Okay. So calculate the Grundy values recursively. We have A and B, right? We can say f of, so let's say int low or min or x, yeah, so lower or lower. I'll just say low is A is what value? A plus 1, and B doesn't change, and the total is decremented by A. Right, we select A. There's low, there's high, which is the other way around. We don't touch A, but we take B minus 1, total minus B. Then there's 4, so we say vals dot insert low, vals dot insert high, and then we say for each int I equals A plus 1 to I is less than or equal to B minus 1. We're going to increment I, and we say take the XOR of these Grundy values. So say left, right, and we'll say vals dot insert left XOR right. So the left side is going to be f of A to I minus 1, total minus I. All right, so we pick I, take total minus I. The right side is going to be similar. It's going to be f of I plus 1 to B. Now, I minus 1 can be A, it just itself, but it won't be less than A. And similarly, I plus 1 can be B, but it can't be greater than B, right? Yeah, so left and right, XOR left and right. And then we have a low, we have a high, I have left and right, calculate the mex. I'm going to say for int I equals 0, so I is less than, I guess, the largest value in this set. I don't know how big these Grundy values can get. Kind of wondering if I should make a actually, you just use a while loop here. Yeah. Say if vals dot count of I is equal to 0, and we break. And otherwise, keep incrementing I. So actually, you can use a while loop. You could do for int I equals 0. Well, you want I to be up here. Int ret. Say vals.count of ret equals 0. It's greater than 0. Increment ret. So you start off at 0. If 0 is there, you increment, and you just keep going until you get a value that's not there. There you go. There you have your recursive Grundy function. What happens if we do this? Wait, what? Redefinition of I? Where? What? Oh, that's fine. Typo. Runtime error. No. No. I don't think we have if it's equal to 0 what we should return. The total is 0. No, it should return 1. So this is 0. This is false, it'll exit. If 0 is there, it'll go to 1. If 1 is not there, I think this is the Stack Overflow. These gnats? What is going on here? I don't want gnats in my room. I don't want gnats in my room. Oh, you know what? I do have some garbage I gotta take out. Huh. So this is going on infinitely. Why is that happening? That's not supposed to happen. This is definitely not supposed to iterate infinitely. I don't know why that's happening. Oh. TLE on 5 million. What is going on? What is going on? That's not supposed to happen either. It's definitely not supposed to go to 5 million. We're supposed to go up to 100,000 or so. Why is this? What's going on here? Oh, we need a bunch of cases here. Excuse me. Desired total could be 1. Choosable integer could be 1. Alright. Is it, do I need to memorize these things? I don't think so. I'm wrong. Really? True, true, false, true. 10, 11. Alright, let's focus on that. So this is relatively quick, but I'm definitely very confused. I'm guessing maybe I'm supposed to memorize. I don't think so though. It doesn't seem like you'd be looking at the same thing over and over again. But maybe I do need to memorize it. I don't know. We'll look at that in a minute, but this should be at least correct. So that's confusing as well. Yeah, I don't think I'm doing this correctly. I think the base case is off. So 10 to 11, desired total is 11. What happens? We say low and high, we take a plus 1b, total a minus a. The total is 11. Subtract 10. And that low, we do that recursively. That total the max value for when you subtract, when you pick, the max value for when you pick 10, you have, no, excuse me, you pick 1 on that one. So you have 2 through 10, and the total is 9, and you have a losing state there, I think, right? 2 through 9, and the total is 10. Oh, that's interesting. 2 through 9 and the total is 10. And then if you take 2 through 9 and the total is 10. Oh man, this could be kind of involved. I think maybe I do need to memorize this now that I'm thinking about it. Now that I'm thinking about it, I do think I need to memorize this. It's gonna be really expensive if you don't memorize it. But anyway, so 2 through 9 and the total is 10 now. Do that recursively a few times. Then you go 2 through 9 and 8, and 3 through 9 and 2 through 9 and 10, 3 through 9 and 8, 4 through 9 and 5, 5 through 9 and 1, and you have a negative number, 4 through 9. Here, 5 through 9 and negative 3. So at this point we say we lost, right? That's a losing state. 5 through 9 and a negative number. That means the opponent won, right? So this is a losing value. Alternatively, we said if no matter what the total is, so if the total is not less than 0, this actually, this is kind of tricky too, because if the total is equal to 0, then I actually need to return 1. You could be in a position where A is greater than B. Like if you're looking at 5 and 5, in other words, if A is B and A is the total, that's a winning state. The next state is a losing state, even though the total is not less than 0. So that's kind of a question. These cases would fail if you said less than or equal to 0. Then, see, that's a little confusing, right? That's actually a winning state. If, well, you could say, or let's say total equals 0. If the total is equal to 0 and so that's super confusing. Yeah, I think it's just the same thing. So, or the total is greater than or equal to 0. Total is less than 0. I mean, you lost, right? The other player put you below. They already won. But if you're at 0, the other player can put you at 0. See, that's really confusing. That is really confusing. Player first caused the running total to reach or exceed 100 wins. I want to say that if you're looking at 0, you always lose. Let's just say if you're looking at 0, you always lose. And if you have no moves, then you also lost. Let's keep it simple. Just edge case. Let's do it this way. So if you're looking at the total of 0, that means the other player already won. Yeah. I don't know if that works. I don't know if that makes sense. I don't know. I'm kind of struggling with this. Feels like it should be able to include this edge case in the logic, and without it, we have problems. It's the sense that I get. Now my question is, why doesn't this work? It's kind of a lot that happens here. Maybe we can make things simpler. We can go like 4 and 5. It's better. True, true, false, false. 4 and 5. Could actually go through 4 and 5. So if we have 4, 5, then we go to subtract 4. It's 3 and 1. No, excuse me. It goes to, so 1, 1, 4, 5. Low goes to 2, 4, 3. Low goes to 3, 4, 1. Low goes to 4, 4, negative 2. So this is 0. So 3, 4, 1, G 3, 4, 1, we get low is 0. High is 3, 3, negative 3, 0. And whatever this recursive amount is, the max is, oh, actually, no, we do want to figure out what this is. So low, high, left and right is going to be in the XOR. So the left is going to be oh man, it's so much calculating. Okay, we definitely want to use memoization, brother. This is a crazy amount of calculating. Alright, let's just print it. Just print out. That's way too much calculating. That's worth. Can we do, let's do 3 and 4. Let's make it even easier. Wow, I've been on this almost over 2 hours. Alrighty, so 3, 3, A, B, B, total, total, red, red. Alright, so 3, 3, 1, get G of 1. 3, 3, 1, we get G of 1. A is 3, B is 3, total is 1. A is 4, B is 3, total is -2. G is 0, right? So you have no moves, but your total is -2. Okay. 3, 2, total -2, no moves, G is 0. 3, 3, total 1, G of 1. So this 3, 3, there's a low and a high for 3, 3, right? A goes to 4 if you pick A, B goes to 2 if you pick, but either case you pick 3. So in both cases, yeah, you get this 1. You get the low, the high, or zeros, and then there actually aren't any other values to pick here. So this is a winning position. Whatever player is looking at that, that's a winning position for that player. Okay, same thing. You get A is 2, B is 2, total is 0. Now where does that come from? A is 2, B is 2, total is 0, G is 0. But I think this should be, yeah. If the total is 0, then basically someone already put you at that spot and you lost already. Right, you're coming into that spot, 2, 2. So there's 3, 3 here. I don't know where this 2, 2 comes from. Because the other player already reached it, right? That's pretty much what that means. The other player already reached 0. 2, 2, 0. Lose 2, 3, 3. How many things are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 calculations. Let's see if we can make that happen. I think we can handle this. Actually, I want to just fix something here. Oh. All right, I want to take a look at not 10, 11, that's too hard. 3, 4. 3, 4's got 15. 3, so 1, 3, 4. Okay. So the low and the high. So all these different numbers, we get G of 0, 3, no, excuse me. We get G of 2, 3, 3. G of, take the max of these things. G of 2, 3, 3. 1, 2, 1 is the high, and the values in between we say G of 2, which is 1, 1, 1, 4 minus 2 is 2, and 3, 3, 2. So we pick 2, we subtract 2, and we go 1 to 1 and 3 to 3. Right, A goes to 2 plus 1, and B goes to 2 minus 1. B got 2 minus 1, and A goes to 2 plus 1, right? Okay. And you take the XOR of these integers, these values, nim values. By the way, this should be 0. Expecting this to be 0 because we cannot win this game, right? It's not possible. We use all of our moves, we will never make it. It's not that we'll use all of our moves and never make it, it's that the other player is going to win before we win. If we pick 1, they pick 3. If we pick 3, they pick 1. If we pick 2, they pick 3. And that's it. They win. Okay, anyway, so, alright. So 2, 3, 3, we would say, same deal, we have the low, we have G of 1, 3, 1, we have the high, G of 2, 2, 0, we have G of and now what does this say? This is I is A plus 1 and less than or equal to B minus 1. So A plus 1 is 3, less than or equal to 2. So that just doesn't happen. That just doesn't happen. It's 2, 3, 3. So 1, 3, 1 we could look at. So 1, 3, 2, 3, 0. That's the low. The high is 1, 2, negative 2. And then these are G of 2, right? 1, 1, negative 1, XOR 3, 3. Zero. Or, yeah, negative 1. Subtract 1, subtract 2 in both cases. Okay, that's 1, 3, 1, 2, 3, 3, 1, 3, 1. And all of these go to 0, I think, right? This is 0, 0, 0, 0, 0. Nice, that's resolved. Okay. Yeah. So these are all losing positions. Correct. 1, 3, 1. So 2, 2, 0. Also, this is 0. This is a losing position. So this is 0. So, okay, what's interesting about this is that actually this is a 1. Because all of these are zeros. This is going to go to 1. And that means that this goes to 1. And that means that this goes to 2. Right? The way the mex works. Take the mex of basically just 0 for 1, 3, 1. So we have that for 1, 3, 1, right? It should be 1. Okay, I don't see 1, 3, 1 anywhere here. What happened? Excuse me? Excuse me? Excuse me? You what? You what? What in tarnation? I don't see a 1, 3, 1 anywhere here. 1, 1, 1, 2, 1, 0, 1, 1, 1, 3, 4. Whoa. Uh-oh. My hand calculation doesn't match what my code is doing. How did that happen? Shouldn't there be, yeah, there should be a 1, 3, 4 here at the bottom, right? Geez, 3. Expecting that to be a 0. We get 2, 3, 3, 1, 2, 1, 1, 1, 2, 3, 3, 2. So 2, 3, 3 should be somewhere here. I don't, oh, there it is. 2, 3, 3. 1, 2, 1. 1, 2, 1 comes from selecting 3, subtracting from 4, and then decrementing b over here. Right? B minus 1 minus b. So that should be 1, 2, 1 somewhere here. 1, 2, 1. There you go. Let's say negative 1. That says 1. Okay. Okay, 2, 3, 3. We should get 1, 3, 1 and 2, 2, 0. So 2, 3, 3. See 2, 3, 3. Yeah, okay. So 2, 3, 3 should give us 1, 3, 1, right? A plus 1 goes to 3. And oh, 3, 3, 1. Wait, what happened? Happened there. Why do we get 1, 3, 1? I don't know, but that should be 2, 3, 1. Not a 1, 3, 1. No, 2, 3, 3. It should be a 3, 3, 1. Whoops. Oopsies. Sorry, my mistake. 3, 3, 1. Oh no, it's all different now. It's totally different now. Uh-oh. Uh-oh. Okay. Completely different. Do we have 2, 2, 0? I think we do. 2, 2. We have 2, 3, 3 and we have 2, 2, 0. 2, 2, 0 and 2, 3, 3. Okay. 3, 3, 1. We get g of 4, 3, negative 2. G of 3, 4, negative 2. And that's it. Those both give you 0. This gives you a 1. Gives you a 1. So 3, 3, 1 is 1. 2, 3, 3 is 2. This is a 2. All right. 1, 2, 1. We get 2, 2, 2, 0, which we actually saw already, right? we get 1, 1, -1. These are ending states. That's it. Yeah, that's it. So this goes to 1. So this is a winning state for whoever's in it. These are losing states, so whoever's looking at those. So 1, 2, 1 is a winning state. And then 1, 1, 2 XOR 3, 3, 2. 1, 1, 2, 3, 3, 2. So 1, 1, 2. We get of 2, 1, 1. And 1, 2, 1. Now this is kind of interesting. This is definitely a 0, because the total, yeah, A is greater than B. And then this is 0 as well. Oh no, this goes to 0, I think. It's decrements. Yeah, A is greater than B, so you go to 0. No matter what the total is, you go to 0. Alright, because the total is 0, then yeah, but right. Right, okay. So these give you zeros. Now what's interesting is that makes this a 1. Now, I'm a little bit confused about this. I want to say, see, this is the interesting part. If B, I think this is the issue. Right? If we go to 1, 1, 2, it should give us a 1 here. Yeah, see, that's wrong. That's incorrect. That actually should give us a 0. And the reason that matters is because if this was the 0, I think what's going to happen is, so 3, 3, 2, well then that gives us a 1. 3, 3, 2 is, does that give us a 1 also? I think so. Yeah, 3, 3, 2 is actually a 1, because that's going to give you 4, 3, -1, which is 0, and also 3, 2, -1, which is also 0. So this gives us a 1. So when you XOR these two, this 1 and this 0, you get a 0. This 1 and this 1, you get a 0, which then puts this at a positive value, puts you at 0, 1, 2, 3. That's why you get 1. That's why you get 3 instead of 0. So we need to handle this case correctly. Somehow we're not. Now it's a little weird. Why is this not handling this correctly, though? These states don't even exist. That's the thing. These don't even exist. They shouldn't. These aren't even transition states you can go to. This A greater than B. So what we can do is we say, let's do it this way. If these states exist, so if A plus 1, really it's if A equals B, otherwise you would do it this way, right? That's kind of what it comes down to. So A equals B, and then we'll set if A equals B, you're going to say, you're going to return so if the total is greater than B, you lose, right? Total is greater than A. Just as an integer, total greater than A or B. Okay, because here's the deal. So you either lose or win here. If the total is equal to B, then you've won, right? You're in a winning state. The next transition state is a 0. You return a 1. True, convert that to a 1. If the total is greater than B, you can't win. You lost. So total less than or equal to, or B greater than or equal to total. Now, I don't know about this, you know. A little uncertain about this one. I think we need to do that. There we go. Okay, that's better. All right. Yeah. Just got a little too confusing without doing it otherwise. Let's see if we need to memorize this at all. Okay, so we still have TLE. Let's try some of the shorter ones. Still the first one, 10 and 11. Oh no, really? Why does this work? Why? Oh no. Alright, how about, so we did 3 and 4, let's do 4 and 5 now. Very similar situation. 5 and 6. Why does it all of a sudden stop working? 10 and 11. No, please, come on, give me 6 and 7. Give me something I could do by hand, man. Give me something I could work with. Okay, this one. It's better. Not much better, but it's better. I really think this total equals 0 is going to give me issues. I think that's going to be the problem. I wonder if... I wonder if this ever happens. I don't think it does. Alright, it's like somewhat reasonable, I guess. So what do we expect for... We expect 0 for our run D value for 6, 7. Yeah, 1 through 6, 7. It should be 0. We get 4 though. Alright. Something along the way is coming off with a 0 when it should be giving us a value. We could look it up. We could find out which one. But it's not due to this A greater than B issue. So that's kind of interesting. I think it's because of this total less than or equal to 0 issue. I think that's the problem. So we do 266, 1 5 1, and then we have a whole host of things that we take the XORs for. 2 is 1 1 5 XOR 1 1 5 XOR with 3 6 5. 3 is 1 2 4 XOR 4 6 4. 4 is 1 3 3 XOR 5 6 3. Alright, we picked 4, we said. Yeah, 4. 5 is 1 4 2 2 5 6 2. I'm sorry, 6 6 2. We already did the 6. There should be 1 2 3 4 5 6 of these. 6 of these, and all of them should be positive values. So 266 we can see we get, so one of these should be 0, I guess. That should be the one that's a problem. So what do we say this is? 266? Somewhere around here is 266. Excuse me. Alright. I'm going to cover my mouth, but I'm on the hunt here. On the hunt. 2 5, that's not what we're looking for. 2 2 2 3 2 4 2 6 2 6 6 3. Okay. 1 5 1. We're going to use red for these, or green, or orange. Something to note that it's not exactly what it's supposed to be. This is just supposed values. So 1 5 1 should be here somewhere. 1 5 1, we got a 1. 1 1 5, we get, there should be a 0. Absolutely should be a 0. Somewhere is a 1 1 5. Just look for the ones. 1 1 negative 1. 1 2 1 3 1 5. where's the 115? 124. 1 2 3 1 3 1 1 0. Do we not get a 115 here? You pick 2. I is 2. Starts off at A plus 1, just 2. And you get a 2. B is 7. So this is 2 to 6. Right? Left side is 1. 2 minus 1 is 1. Total 7. No, B minus 1 is 5. Excuse me. Alright, it's going 1 to 6. So it's 2 to 5. 7 minus 2 is 5. So there should be a 115 somewhere in here. Definitely should be a 115 somewhere in here. Oh. Yeah, that's what I'm missing that. There it is. That's why I'm missing that. Okay. Should be a little bit easier to find. There you go, 115, we got 0. Which is correct, I think, right? You can't win with just a 1 and 5. 3 6 5, we got 1 2 4 it says. Yeah, 1 2 4. Sharp 1 2 4. 3 6 4. Which is 3 6 4 is 2. Oh. We need 1 2 4. Or 4 6 4. 1 2 4 or 4 6 4. 4 6 4 is a 1. And a 1 2 4 is I don't see 1 2 4. 1 2 4 is also 1. Uh-oh. That's the one. That's the one. Okay, that one's a problem. The other ones might be a problem too, but we'll start with those two. So 1 2 4 and 4 6 4 both being 1 is not going to work. So those are both winning states. 1 2 4 and 4 6 4. What happens? Well, yeah, clearly 4 6 4 is a winning state. But 1 2 4 is definitely not a winning state. That should be 0. Yeah. How come this is not 1? That is not a 0. This makes sense that it's a winning state. It's a 1. No matter what you pick for 4 6 4, you get winning states. So if you do 5 6 0, right? That's a 0. you get, if you do 4, 5, -2, that's a 0, and then 5, you have XOR with 4, 4, -1, and 5 is 6, 6, -1. And these are both zeros. And so this whole thing's a 0, so this is a 1. Two, 2, 3 gives you a 0. Oh. What? I think part of the issue is there's another calculation that happens here. I think you return 0 if there's no possible way to reach the total. I think that might be the problem. But you can use the difference of sums for A and B to do this. Yeah, I mean, okay. Yeah, because if you do the normal approach here, that assumes you're kind of taking, yeah, it's kind of a weird thing that goes on here if you can't get to the end. I don't know, it's a little bit unusual. But you could say if b times b plus 1 divided by 2 minus a times a plus 1, really should be minus 1, divided by 2, this thing, if you get that sum, if that is less than the total, turn 0. Now, you know, I don't know how I feel about this. There we go. Yeah. It's kind of this funky thing that happens where you are not, you're not going to actually execute all of the turns after that, and it gets kind of funky because those are states that should end right there as like ending states, I guess, something like that. It's a little weird. TLE. Okay, we probably shouldn't have all the debug statements in there, but let's grab like 10, 11. Try this, see what happens. 20 and 21. Wrong answer. Oh man, come on. Oh, gotta be kidding me, really? Oh, why it's so hard? This is too hard. Really? Really? You have got to be kidding me. Why? Why you give me a wrong answer? I don't know what's going on here. I think the theory is correct, but I just can't seem to. There's something going on, man. Some funky thing going on. Funky. Some strange thing going on here. It's got to do with my base cases. I know it does. I know it's got to have something to do with my base cases. 13, 14. So many ways this could be wrong. It's gonna take a while to debug. I don't think we need this anymore, by the way. Oh boy. 2,500 more. Nice. So it's supposed to be 0, doesn't come out to be 0. Why though? Why? Okay. 13, 14. What could it be? What could it be? What? Space cases, man. I don't know. It's super awkward. It's just. Okay. 1, 13, 14. Alright. So there's a few different scenarios. 13 numbers to pick from. 13 possibilities here. So. Excuse me. One of these comes out to be a 0, though. 2, 13, 12. 1, 12, 1. It's definitely a 1. 1, 1 cross 12. 2, 3, 13, 12. 1, 2, 11. Cross 4, 13, 11. 1, 3, 10. 5, 13, 10, 1, 4, 9, 2, 6, 13, 9, 1, 5, 9, 7, 13, 9, or 8 rather. Make those lazy 8s. 1, 6, 7, 2, 8, 13, 7, and 1, 7, 6, 2, 9, 13, 6. So these after this point are all after this point these are all winning positions, right? Yeah, 1, 7, 6, 9, 13, 6, 1, 8, 5, 10, 13, 5, 1, 9, 4, 11, 13, 4. I realize this is getting a little bit out of hand here. I think the reason my neck is aching because I'm leaning on my shoulder like that. 110, 3, 12, 13, 3, and then 111, 2, 13, 13, 2. Okay. So these are all winning positions, certainly. Like immediately winning. Excuse me. These are all just ones out the gate. Because anything you pick is going to be a winning position, be a 0. These are also winning positions. They might be 0 or 1, I don't really know. Definitely greater than 1. 2, 13, 12, okay. Let's go through this. So let's print all of these. You know what we can do? We can make this a lot easier for ourselves. I can make this a lot easier for myself by printing only the information that I need. Just print all this information. Find the one that's a 0. Just take all these, yeah, left, low, high. So we'll say these vowels. Yeah, so we'll say if A equals 1, B equals 6, or what is this? 13, total equals 14. Say if left, right equals 0. Basically this information. Left and right a and I minus 1. So I plus 1 is b. And then we have low, high, same thing. If low equals 0. Oh, we really don't need this, do we? Well, okay, sure. This is just a plus 1 and b. No. Minus a minus I. And this is high. This is a, this is b minus 1, and total minus b. Okay, this is, you don't really need that anymore. Alright, let's just compile. Just see if we compile here. Okay. What is, can we exit this? What is this? What did we do? Hello? Come on, stop. Just hit the wrong button, all of a sudden it's like won't. Okay, there we go. Alright, whatever that was. Whatever that was. Okay. I need to go to bed. I was not expecting this to take this long. This is taking a very long time. 3 hours now. Spent debugging this. Okay. 149 and 613.9. This is why we failed. It's like, you gotta be kidding me. 149 and 613.9. Of course. What? 149 and 613.9? It's supposed to give you 2? No, dude. No. No. Absolutely not. No. Stop. I think the problem is you can have multiple games that get the same number. I mean, we need every game to have a different number. That's part of the problem. It's part of the problem. Ah. Ah. Mm, maybe this is not an impartial game because of this piece here. It's so confusing. I don't know, man. I gotta lay down. I'm losing it. Struggling. Definitely struggling. Man. And how... What do I even think about all of this? Oh, you gotta be kidding me. No! 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 Excuse me. Yeah. I would be kind of upset if Grundy theorem didn't actually work here, and it's just been spinning my wheels. It's so close though. Like how? It's so close. What happened? Why? Why is it working? No! You gotta be kidding me. What do I even think about here? Well, excuse me. I think I'm correct about the different games that are set up. So the Grundy value will be recursive, and it's going to be, we're going to say each game is consecutive numbers, and a total. Alright, that's fine, that works. And so now you have the edge numbers you take, and you get a single game in each of those cases. So the largest number and the smallest number of your consecutive numbers. And then you also have all of the numbers in between, and that gives you two independent games. You take the XOR of those two independent games, and those are your values. But I think the thing I'm struggling with here are the base cases. It's like that's all well and good, except
What about when you're looking at 0 through or 1 through 10, the numbers, and you're already at 0. Excuse me. The total is already 0, and you're already done. And you would say, well, if the total is already 0, the game needs to be a 1, right? You need to return a 1. But what if you But what if, I guess it's just a 1 then, yeah. Because any position you can go from there to 0. So that makes me think total's got to be less than 0. And you return a 0 if the total's less than 0. Yeah, you've already lost if it's less than 0. Now, if you're presented with a total that's 0 and no moves, see, that's a question. Can you see if you do the total is less than 0 as the state, and then to get return 0, and then but A and B if you don't have any moves left. See, that's a good question. So if you did like 1 0, so you have 1 move and you're at 0. That first move basically is just only 1 move, and it's the left and the right are the same thing, I guess. Both of those return 0, so then your max would give you a 1. There wouldn't be any inner loop either. Or not, yeah, no. I mean, yeah, I guess if A is less than, if A is greater than B, you could return 0 also. If you don't have any moves to make, I think you're always returning 0. Let me think about that. If you don't have any moves to make, are you always returning 0? So if you have 5, 5, and 5, right, then it's only 2, the high and the low should give you no moves, but we're at 0. So you, looking at 0 without any moves, lost. But the person above you, before you, made that move to put you there, won. I think if you don't have moves, you're always 0. Always returning 0. Yeah, this base case is super confusing. Okay. I think it just, I don't know what I did. I think I kind of outsmarted myself, I guess. Not outsmarted, but what do they call that? I confused myself. Yeah, that's the right word. I overdid it, and then I caused problems. I don't think we actually need this edge case. Excuse me. I think actually if we try to handle that edge case, run into problems. Oh. All right then. I think there's multiple edge cases that we try to handle them, run into issues. We don't need this anymore either, I think. It's just for debugging purposes. I think it should just TLE, right? Runtime error. Stack overflows. Total is less than 0, or A is greater than B, and we return 0. And that's basically it. You're always going to hit one or the other, but now we're wrong. But now we're wrong. Why? No. Come on. Why is this wrong? Oh, I'll come back to that. I don't know, man. Okay. These are true. But this one's false. This 1011 is false. I mean, what? You what? You what? So it does handle these edge cases. Yeah, I don't know why. I think it would. About 3-4. Kind of expecting this to work. Kind of expecting this to work. Now, why wouldn't it? About 2-3. How about that one? Does that work? Okay, 2-3 works. 3-4 does not work though. 3-4 should give us 0. 3-4 would be why does the base case fail? I think it's an issue with the base cases, which is so weird. So 1-3-4, we should get 1, 2-3-3. 3 gives us 1-2-1, and then 2 gives us 1-1-2, XOR 3-3-2. Okay. What do we expect for each of these? Well, 2-3-3, we would say, well, what do we get for each of these? How about that? Just do something like this. Get our debugging code here. This is 1-3-4. The other one is 1-3-4. Which ones of these are failing? We'll find out right now. Okay.
This left and right is failing. The low is 0. This is also wrong. It should be only for the ones that are giving me issues here. So both the low, the left, and the right all give me 0. You gotta be kidding me. Why did 233 give me 0? God, kidding me. Okay. 233 gives you 0? What is that? Use 2, you go 3, 3, 1. If you use 3, you go 2, 2, 0. There's no in between. 3, 3, 1. Similarly, these are all going to give you 0. Now, see, that's incorrect, right? Yeah, the base case is wrong. Because now this 3, 3, 1, we go, no, this should be fine, right? I mean, this should be, 4, 3, -2, and 3, 2, -2, right? Which both of these are zeros. This should give you a 1. Now we're fine. Right, which is true. And then this one, same deal. Well, actually, this is an instance where you've already won. So no. Because what would happen is this should give you a 0. This is a losing state for the opponent. That's kind of what I was getting at before. If you're looking at less than or equal to 0, that's confusing. Right, but this left-right still has issues. I'm upset. I'm upset. If you're presented with a 0, it's definitely just a 0, right? So now this one's not a 1, but a 2. But then that runs into issues of, but now if you do, 10-0, you're going to get the wrong value. You get the wrong value for 3-4 also, but 10-0 is not going to work anymore if you do it this way. So you can kind of handle that by just taking care of this edge case. Still like really frustrating, I guess. Doesn't quite work how it's supposed to. Base cases, man. What's wrong with these base cases? So then somehow both of these end up at 1. So 1, 1, 2. We get left, right, left, and right. And both should give us 0. puts this at a 1, which is wrong. As I was kind of getting at before with the base cases are really funky. So now you have to handle this case where you can't win here ever. This actually has to be a 0, really, because even though you kind of have to stop when they're equal to each other, when A is equal to B. Otherwise, you end up with 1 extra. So I got this base case. Then you get another base case of like, if they're, if you could never end the game, you get a similar position. No! I'm tempted to just see the discussion and see what people say about this. But yeah, it still doesn't, no, no. This doesn't work, man. This does not work. 10, 11. I could change this to 10, 11 now. I feel like it's really close, but it's just too many issues with the base cases. So 1, 3, 7 and 5, 10, 7. What happens there? We don't need all this anymore either. Um, 1, 10, 11. I'm looking at 1, 3, 7 XOR 5, 10, 7. And both of these give us 2. That gives us a 0 that we're not supposed to have. So we would go, well, we can look at this, 2, 3, yeah, 3, 7, 5, 10, 7. I don't know what these are supposed to be. They're both not supposed to be equal to each other. 2, 3, 6. Well, we can look at 3, 7 and see what we get. What do we expect? Output true, expected false. Okay. Brother, man. It's challenging. Okay. 2, 3, 6, 3, 1, 2, 4, and then what is this? If you put 1, 1, 5, cross 3, 3, 5. So both of these give you zeros. Let's get a 0 there. So 1, 3, 7 should be 0. So that's immediately wrong here. But, I mean, well, that's okay. I guess we get not a 0 over here. Oh, no, wait, what? 3, 7 should be false. We got true. Why do we get true? This should be 0. Yeah, this should definitely be 0, right? You can't, there's no way you get to 7 from here. But one of these gets a 1. This should also be a 0, right? There's no way to get to 6 from 2 and 3. And this should also be a 0. There's no way to get to 4 from 1 and 2. These are all zeros. I'm so confused. But then this gets a 1. So I think that's part of the problem. That was the other one that I was looking at before. The base cases. You can just never reach. I mean, we added that already before. I'm so confused, man. Like, I don't know. I feel like I'm getting the same thing I just had before. It's exactly the same thing. What is going on? Yeah, if you're just less than the total, you just always return false. Always return 0. Sitting here crying in my prom dress. I'd be the prom queen if crying was a contest. Catch him. What's up, Yuki? What is this? Oh boy. Dancing emojis. How are things? How are you? Welcome back. I need to go to sleep. I'm freaking exhausted. Losing my marbles though with this problem. So, watch this. Just immediately breaks. Doesn't work. Doesn't work. Decided to spam auto on everything I can. Yeah. How's your day been? It's been alright. Thank you for asking. I talked to my mom. Didn't go to church, but watched church online. Watched the congregation online. Shared some opinions about the gospel to some folks online. There's a fellow who was a trucker from Europe. He's retired, and he said he was retired for I think he said 10 years now, or he retired, yeah, and he's been looking into different texts about spiritual texts. So he's looking at things like the Quran, and I think he looked at some other things too, a little bit about the Bible. I think he knows more about the Quran than he does about the Bible, though. So it was interesting conversation. I kind of had I guess I have a new pen pal, something like that. He gave me his email, so could chat. But what else I do today? It's been good, yeah. I spent a lot of time on this problem already, though. I watched a bunch of YouTube videos, just random stuff. 3.5 hours while I was on this. It's cool. Thanks. Yeah, it was pretty. I was like, yeah, it was kind of cool. It was kind of unusual. I don't know. I kind of didn't expect anything from my YouTube channel, quite frankly. So yeah, that was really neat. And Yeah, there's like a lot of topics to talk about though with him. A lot of things we disagree on. A lot of things I think he's not aware of also. Which is great. I mean, it's fine. You know, is what it is, right? It's like that's kind of the thing with. I mean, it's not fine, but it's like it's fine in the sense like you don't need to know everything, but you do need to know the gospel, and you do need to believe. You need to repent and believe. Those are the two things you need. Otherwise, you go to hell and burn for all of eternity, and it's a tragedy. You make a sick teacher, by the way. Thanks, thank you. That's a nice compliment. I don't know. I don't know. I mean, I'll just say thank you. I don't know. I believe it or not, I actually was thinking about that today because I was like, man, like, so like what I'm looking at right now with this problem, basically, I also it's kind of awkward because I might be wrong about this, but pretty much the like the deal is, I attended university. I went there for like years, and I spent a lot of time learning about like trying to figure out how to solve these Leetcode problems, and they're pretty hard. And the reason I did that is because I wanted a job as a software developer, and the reason you need to know that information for a job as a software developer is a lot of the big companies that pay really well give you these programming questions as like part of the interview. And as it turns out, after all these years of studying, I learned that realistically, these are basically competitive programming questions. And so really what you're looking at is a small competitive programming contest for your job, which is sort of okay, but it's also really a big problem because you don't learn any competitive programming at university. And what ended up happening is that I ended up spending like years, and I'm talking like 8 years, like literally while I was still at university, I was spending huge amounts of time trying to solve these difficult maths questions online, basically these competitive programming questions, without knowing these are competitive programming problems, which basically means that I was trying to reinvent the different techniques here from scratch, which like a lot of these techniques literally could have been like PhD papers. So basically what I've been trying to do for the past 8 years was develop PhD theses without knowing them on my own. or substitutes, which is like, right, that's a horrendous waste of time. It's kind of the position I ended up finding myself in and not realizing it until pretty recently that like this is what I've been doing. And the tragedy is like, unless you want to be a teacher or a professor, right, a PhD professor, that's a horrible waste of time. And I've wasted a lot of my life. Like I've wasted my youth, like a huge chunk of my youth, like 8 years of my youth basically wasted kind of just trying to reinvent things that already existed that would take a really long time to figure out again. And that's like really sad. That's like really sad to think about. I heard that those interviews can be super toxic. Yeah, they can. Oh, really? Toxic? That's interesting. Do you mean like toxic as in like the person interviewing could be toxic, or do you mean like just really hard? Because they can be, yeah, they can be really hard, and people get really frustrated. Like, do you mean just like it causes frustration, like for the person interviewing or the person getting interview? The interviewer or the interviewee. A bad way of interviewing people. Yeah, exactly. Yeah, well, I mean, the complaint that I have is like, it's fine if you want to give people competitive programming contests for jobs. Like that's all. Well, I mean, that's your prerogative, but not knowing that that's what you're getting yourself into, and that that's not what they teach at university, could put you in a really bad spot. Like me, it put me in a really bad spot because I ended up spending inordinate amounts of time studying things, not even studying things, trying to figure out things from scratch that have already been figured out a long time ago. Like basically, if I had studied, 3 months of competitive programming questions, literally just went to this website and went through each of these pages and learned what to do, Now, obviously, I'm struggling right now in this case, which is kind of unfortunate. But in theory, I'd be prepared in 3 months. I'd be 1, 2, 3. It's basically just memorizing other people's PhD theses, which is not that hard. But if you don't know that and you try to develop these things on your own, thinking that all it is just a test that you're prepared for already, or whatever, you just need to spend time studying, like not studying, but just try to solve these problems. Like you're going to be like, yeah, there's just a huge difference there. That's like, it's actually upsetting to think about that I wasted so much time. Yeah, that's yeah. So I thought about that actually. Maybe I should become a professor because I would actually redeem some of that time that I spent. Right. That's kind of, yeah. Since most people don't learn the stuff they need from school. Yeah, exactly. Yeah, that you nailed it. That's exactly why they're not good. That's exactly why they're not good. No, most of these things. I mean, I learned some of these things in school, but hardly any of it. I shouldn't say hardly any. A good chunk of it I did not learn in school. And like Sprague Grundy I didn't learn in school. So Josephus I didn't learn in school. I actually still don't really fully know it. Scheduling jobs I didn't learn in school. I still don't fully understand those either. There's a bunch of stuff. Just thinking, some of these things technically I learned, but I wouldn't really memorize them. Probably not. The graph stuff, I actually did take a class where it covered graphs. Most of these things are covered. And did a little bit of geometry, but like not all these things, I guess. I mean, a good chunk of the stuff is covered in school, but like, okay, string processing, I don't think I did any of this in school. Like, I did all this stuff. I did study this stuff on my own afterwards. Aho Korosik at KMP, Knuth Morris Pratt, Robin Karp is another interesting one. I don't think I really know too much about Robin Karp, but there's like, yeah, these things I learned outside of school actually. DP, I mean that's yeah, you kind of learn that in school a little bit. Although it's kind of hard. DP is kind of hard. Data structures. These trees I didn't cover in school. Definitely not. All this algebra stuff. I mean, we did some of these things, but not all of it. I mean, I guess I covered a good chunk of this stuff in school. I guess that's true. But a lot of it didn't. A lot of it, like, it's, yeah, I don't know. It still feels really bad. It still feels like. Plus a good amount of interviews make use of stuff for their interviews that would never be used in their actual job. Yeah, well, that's the other thing, right? It's like your job is not a competitive programming contest, right? Like, it's nothing to do with it. And I think there was a guy who started his own company just basically effectively copying Leetcode. I should say copying. It's not like he copied it. It's not really. It's a competitor to Leetcode, and he's a multi-millionaire now apparently. But he was saying that like he used in his job, he used like algorithm like thinking. Like he can count it on one hand. I think he only said he did it like once that he could remember. Once. All of his, and he worked at Google. Like, that was kind of the selling point for his whole spiel, is that he worked there, so he has enough experience to help you get a job there too. It's part of his sort of marketing, and it's like one time go through all 8 years of practicing. Now, mind you, the practicing I did was like all over the place. I mean, I tried all kinds of different things. I learned all kinds of stuff.
I mean, actually, I put enough stuff on YouTube now where you can see it. Like you can see, I've got like years. I mean, I was doing that sort of thing like for 6 years before I started putting up on YouTube. I was doing it on Twitch actually, and where my videos would get deleted, which is kind of upsetting. But yeah, that's how I built a small audience over there. So it was just day in day out, almost just grinding these problems. But I was doing all kinds of stuff. It's sort of all over the place. But yeah, and the saddest thing too is like, you know, even after you go through all of this and you finally can get your interviews, there's still like basic skills that are not taught at university. So like, I didn't even know what a back-end web server was for the longest time. And this is just like, now I'm just complaining in general, complaining about now I'm just complaining about university. Nginx. Okay. Let's see if I can get something to create a web application, done some research on what makes a good web server, search Facebook, Twitter, Foursquare, software, what is this? Serve content, perform some type of... So basically, like, Nginx is a server. HTTP and reverse proxy server, mail server, generic TCP, UDP proxy server, Igor Syzoyev, long time has been running on many heavily loaded Russian sites, including Yandex, Mail, Rambler, Netcraft. Nginx served a proxy at 22.87% busiest sites in May 2021. Yeah, so serve static and index files, auto indexing, open file descriptor cache. Let me sorry, backend framework. Maybe that's better. I didn't know what a backend framework was. Top 10 backend frameworks. Yeah, maybe that's where I should start. Let me just see. Nginx, largest number. 36%. Apache is top in active sites. 25% Apache. Nginx is 23%. Cloudflare, 17%. And Microsoft, I don't know what Microsoft has, but Apache is another kind of like web server. Backend framework. So software framework is a foundation where developers make applications a faster way. Backend framework. All right. Django, Laravel, Ruby on Rails, Express.js, Cake PHP, Flask, ASP.NET, Spring Boot, Koa, Phoenix. Okay. So the reason why these are important or significant, and like I never learned about these things when I was at uni, which is like crazy. It's insane. There's also Java in here. Java has a backend framework, which is, that was what I was supposed to learn, but I never understood it. So basically, the idea is when you have your web application and you want to basically interact with that web page somehow, like let's say you want to like maybe run some kind of database query or something, like I don't know, maybe you want to like load your profile from Facebook. You would send a message to the web server, and then it would basically get all that data, package it up in a new web page, and then send you that web page, and then that web page would get shown on your browser. How all that's actually achieved, originally it was this thing called CGI, and which is confusing because that's also CGI's computer graphics thing, but web common gateway interface. So execute an external program typically to process user requests. So typically what this would do is your web server would have CGI capabilities
And so when you send something back to the server in an HTTP request, then your backend your web server was programmed in such a way where it would run a CGI script through this basically this piece of technology that was installed on the web server. It was built in the web server. Would then run this code and then send back another, send back to your browser another web page, right? And you load the new web page. And from here, the CGI web servers were improved in such a way to make this a lot more efficient, a lot more fluid. There were a lot of issues with it. And eventually this transformed from just web servers having the CGI capabilities to web servers being compliant with back-end frameworks, which made it a lot more effective, a lot more efficient to do this process of basically sending something, some command or something to the back end, and then getting a response that was intelligible. So you can actually have an interactive web page. That's like extremely important if you want to be a web developer, knowing what that is and how that works. Just like it's really basic, like super basic thing. I never got that in my 6 years at university. Never got that. Never understood it. Never was explained. Never, like, such a simple thing. Like, here, how do you, it's very simple. How do I, if I just want to load my web page that's on it, that has my data on a database, like, how do I do that? And that was really upsetting too, because like I'm kind of just like I said, I'm just kind of complaining now. The guy that got a job at Google spent 6 months at a coding boot camp after he got his degree, and he got a degree in maths, not even in software development, where they probably explained, among the things, at least those two things. One, how do you actually write a website to interact with the back end like that, right? How do you, a little bit about back end frameworks and a little bit about front end frameworks, and all the questions that you might want to, basic questions you might want to know and ask to get a job at Google working on the front end. And then the other part was they probably covered the basics of the interview questions, the basic competitive programming things, just enough where he was able to get through the interview. And it's like, how much time I wasted just not knowing things, not like what. Anyway, yeah. So that was also part of my day. It was like kind of fully, because I've been kind of like realizing that as the days go by, as I'm kind of like asking more questions about stuff and spending more time and kind of basically I have some time to kind of like think about my lot in life here, like how did I get here, and I'm kind of realizing like, man, I wasted a lot of time. Wasted a lot of time. But yeah, that was another thing. It's like, okay, well now I finally understand backends a little bit. I can go build something that uses a backend and go show that off to an employer and get a job if I wanted to. But anyway, I'm kind of rambling on about complaints, but I don't know, these things that I didn't know. If someone just explained them, message retracted. Oh no, what happened? C# is superior. I complain too. In Sweden, if you just learn about computers in general, they will teach you that web stuff. Yeah. Like, I don't. In my life, I feel like I was so. I don't know. Like, I don't even know how to say it or describe it. I just feel like I was. Tested the delete button, yeah. Feel like I was left to fend for myself in a way that was really unfair. Because I paid $40,000 for my degree. It's like, if I'm paying $40,000, I would hope that 40,000, yeah. I would hope that they'd at least explain some of the basic things. For us, school is free in Sweden. Yeah, well, that's kind of its own. They pay you to go. Yeah, that's kind of its own conundrum. Even let you get an apartment. So, Europe, taxes are extremely high in Europe. part of that is free school. You have to pay rent, of course. Yeah. So the taxes are a lot lower in the United States. Pay taxes on everything, but I'll take it. Yeah, I won't. I don't want that. So when you're young, it seems really good because you get a lot of free stuff. When you get older, you realize like we're talking for the next 10, 20 years, you're paying that huge amount of tax, and you realize that actually what you got for free and what you're paying in taxes, you're paying like 10 times what you would have paid if you didn't get it for free. So like the 40,000 that I paid, if I pay right now, I pay 2,000 a month in taxes. So we're talking maybe 2 years of taxes, but I'm gonna be paying those taxes for the rest of my life, right? So that's like 20 years, 2,000 a month is a lot more than 40,000. And actually, the school I went to was subsidized. Had a lot of help from the state. It was actually a state school, so it was relatively inexpensive. Actual schools would be like 50,000 a year, but like I said, 2,000 a month, so it's 24,000 a year. I'd say I don't get any raises or anything. 20,000 a year for 20 years, it's like $400,000. So, yeah. Excuse me. So bad with money, it's almost better that they rob me. Going to periods where I spend everything I have, riot points, money. Oh no. Don't do that, man. Don't save your money. Save your money. Just keep it in the bank. That's all you gotta do. Just keep it in the bank. I lost 55,000 pretty recently because I think I mentioned I trade stocks from time to time, and I was doing really well, and so I like basically doubled down very hard, put a lot in. I had 86,000 in there at one point, and yeah, that was a big hit. Yeah, that was a big hit. That was pretty rough. I think I'll be able to make it back though, but like that hurt. Gambling moment. Yeah, kind of. Not really. It wasn't so much gambling as it was like the mistakes that I made were kind of obvious. They were just mistakes. And then I also they were mistakes, and I also I was really distracted at the time, and I should have just like not let myself be so distracted. But I learned some lessons from that. I think those mistakes, I don't think I'm gonna make those again. Like I've been doing extremely well. Like I said, I think I can actually make that back. So I think another video has mentioned like I'm pretty sure I'm on my way to be being a millionaire like pretty soon. I could be wrong about that. I could be totally wrong. I hope I'm not wrong, but I've said stuff like that before in the past where I'm like, oh, I could do this and make a ton of money, do this and make a ton of money. But it's like I always fail. But this time, I don't know, feeling pretty good. So not just feeling. I think I've been doing pretty well. Got a Tesla Roadster. No, I don't even know if I have that kind of money. I don't even know what to do with myself. Like the only reason why I'm trying to make all that cash is I'm like not particularly happy with my job, and I also like it's expensive to start a family, and I feel like I should start a family. So I'm like, I don't have a lot of time to do all these things. So I'm like trying to like get it all together. I don't actually want anything, you know, like that's it. Like I just have like these goals where it's like, okay, you can't have kids unless you can take care of them, and then which I really can't right now. And then I'm not content with my job. It's like I really don't like. There's a lot of things I don't like. So people that do it are the ones that fall and continue trying. I do make it. Yeah, so you'll probably make it. I think so. Yeah, I think I'll be right. I was gonna quit at one point. I actually took a break because I was like, okay, I made back like a huge chunk, and I was like, all right, like I should stop here. just hold on. Just let me reduce what I'm working with a lot and just take it easy. Not be like suffering these huge losses. So you can adopt me. You might be too. Well, I've actually thought about doing that. Like I have a friend who is homeless and a drug addict, and I think he's trying very hard not to overcome his addiction. As far as I know, he's still a drug addict, but I think he told me that he's over it. Like, I don't know. I don't want to slander him, but I also don't want to be dishonest either. So he's an ex-drug addict. Actually, I have two friends, so I'm talking about a different friend. But one of them is homeless, the other one's not. One of them lives with his family. But yeah, one ex-drug addict, recovering drug addict. That's the way to say it. Who's living in like a home, like a halfway house type of thing, and basically I thought I was going to be doing so well at the time that I could put him up in an apartment nearby me, and if I could do that, then I could give him like a place to kind of get himself back in touch with reality, like get himself a job, and then he can start paying the rent that I'm paying for him, and then he can kind of make his way back into society. So that way he's not living in like a halfway house where he's just surrounded by other drug addicts who are going to tempt him with stuff, and like he's not suffering too much, because he was like, also I'm kind of talking very very loudly. He was like basically just roaming around trying to find work with like random people, and he was saying like some of the work he did for someone was literally like trying to get a rat out of their house. Like, and it consists part of it was he was literally just staring at a hole where a rat was supposed to come out. I think he put bait there and he was supposed to wait for the thing to come out and get the bait and grab it, or some craziness. I don't know. He apparently he's also a compulsive liar, so that may or may not be true. Rat, yeah. I don't know what he was, but he described some of the stories that basically he was like scrounging for work, and the work that he was getting was not particularly fun. I think he told me this story about he got like kidnapped by some group of like gypsies that I think he was trying to do like what do you call that, like when you stand on the side of the road and they're going to pick you up to do some kind of like manual labor type of work. He basically did something like that, and the person that picked him up was like basically kidnapped him. They had him do the work that they had to do, and then didn't pay him, and then like wasn't gonna let him go. So basically, like enslaved him. But like they didn't do a very good job because he escaped. He somehow escaped. But they basically that was from what he said. He was saying that like they pretty much were gonna make him a slave, which is like right. I don't want my friend to get kidnapped again. Like it's the kind of things that like he was saying. It's like it's kind of rough. It's very hard to get back to the real world if you were a drug addict and homeless, especially if it's something like heroin. Yeah. This fellow had done crack and heroin, so he's done everything. This guy, he's also in like kind of rough shape physically too. He's kind of got his body's all banged up from some of the things that he did when he was younger. He's got like kind of a busted up back. But yeah, I thought about like trying to get him a place. Like as he said, it's really hard to get back into society, and I thought that would give him a big leg up if I get him into an apartment out here, and get him cleaned up and get him like because if you have a home and you're cleaned up, when you go for a job, you can put down an address, you can get an ID card, you can use your ID, you can kind of get yourself sorted out. But it's kind of hard to do all those things without a home. I guess a halfway house technically you can get sorted out, but the other thing is like it's really sad is that he's getting a significant amount of money from the state, but the house that he's in, the halfway house, is charging him such an exorbitant amount of money that he's getting it's kind of getting nailed. That's the other thing too, is I thought if I could just like give him a ride someplace else, because he's getting I think that money from the federal government, and he can go to a place in the country that's a lot less expensive and then live pretty comfortably. But anyway, yeah, so I have thought about it, sort of quote unquote adopting someone.
I don't know, man. I'll keep you in mind too. If I make that kind of money, I don't know. That's something. Like I said, it's something I thought about. It's like I think it would be a kind thing to like put together housing for people that are really struggling. And I mean people that are like trying to get their life together, but they're just having a hard time um, getting it all together, I suppose. Anyway, that's pretty far off. I'm realistically right now, I'm probably one of those people who needs help rather than someone who can give help. Like I should probably just focus on myself. Wait until I turn 20 so my government can get me a free apartment. Wow. I don't know, man. The problem, like, I know Europeans, they have a very different view of things. I'm telling you, I mean, right now, my government, the United States government, so like you're familiar with counterfeit money, right? Like if someone just writes on a piece of paper, like this is worth $20 and hands it to you, um, usually you would say, I don't want that, right? Abusive home, it's free apartment. I'm sorry to hear that. I'm sorry, man. Oh, I'm sorry. That's really hard. That's really hard. Well, I'm glad that you'll be in a safe place, a safer place. That's yeah, that's really hard. I'm really sorry about that. Um, what was I gonna say? Most empathetic person I've ever seen. Yeah, I don't know. It's a good thing. I don't know. I'll take the compliment. I'll take it as a compliment. Just take the compliment. Thank you. Um, um, but no, I just most people I run into are the exact opposite. Yeah. Well, I think I've said this before. I'm a Christian, right? Anything that's good that you see in me is because I'm a Christian. Um, the Bible says to love your neighbors yourself, and I've been meditating on that a lot lately. And like, yeah, the world's like really, really rough. Like it's really rough. Like I don't know if you just like you fully imagine a world where, because I was talking about like I feel like I've suffered a lot because I wasted a lot of time. And really, the thing that really kind of makes it like hurt is that basically anybody who knew could have just tapped me on the shoulder and said, "Hey, man, you're going to spend 8 years doing this. Don't do that." And I would have saved 8 years, right? So it kind of just highlights that like people are really selfish, like really only think about themselves for the most part, naturally. Aren't naturally good creatures, religion or not. You're a great human. Thanks. Thank you. I wouldn't say I'm great. I don't, you know, I'm not, I wouldn't say so. I'm not there yet to be taking too much praise. If I ever get there, if I'm ever worth praising. Like I said, all the glory is to God, all of the glory is to Jesus Christ. That's the only reason. If I do anything good that's not selfish, that's the reason. But yeah, that's the thing. I've been thinking about that a lot. Like, man, and I was just like that too. By the way, before I was a Christian, like I mean, I'm still kind of like that. Most of the things I do are selfish. Most of the things are with my own, self-interest in mind. Um, Only a small percentage of the time am I looking out for other people. Um, but no, I'll take the compliments though. I just thank you. I mean, I do want to be someone who's like worth praising. That's what the scripture says is be the light of the world, right? Be basically an example of Christ to everyone else. So when people think about Christians, they think about you, and they think about, oh, he's got all these gifts. Should look up Robert Sapolsky. He sounds familiar. Sapolsky, I think. Sounds really familiar. Oh yeah. I don't know if I've showed you videos about Sapolsky, but he's got some really interesting. I don't think he's a Christian, though. You gotta be careful. But he has some really interesting research about animals.
and also people too. Yeah, immigrants from the Soviet Union. Wow. Studied gorillas, right? He's a really interesting guy. He has some very interesting YouTube videos explaining human behaviors. Basically, researches brains and stuff all day. Yeah. Yeah, there you go. Right, brains. Yeah. I've seen some of his videos. Yeah, he's very interesting. He's very entertaining too. Yeah, I'm glad you found him. He's good. This one is cool. Oh yeah, you gonna give me one? Sure. I think I'm probably gonna give it a rest at this problem. I got stuck. I'm kind of wondering now if maybe Grundy theorem is not what I'm supposed to be. I feels like Grundy theorem is what I'm supposed to use here, but I'm starting to feel like maybe that's not right. Or if it is, there's some pieces of it that I'm missing that in the discussion we'll talk about. And I'll be very sad about missing them. Yeah, this is the other piece. It's this guy here, but no, there's yet one more thing that I'm missing in these base cases. Let's see, hold on. If we do 13 and 14, and then also 13 and 14 here. Yeah, I'm distracted. The biology of our best and worst. Do you get the link? No, I didn't. Biology of our best and worst cells. It's the title. Oh, yeah, I'm distracting you from your problems. I took over the stream. No, don't worry about it. I was stuck already. I was already stuck. I needed a break. But no, I like talking to folks. I mean, I don't really know what I'm doing anymore when it comes to like streaming this stuff because, like I said, really, I don't intend to work at Google anymore. Oh look, it's my stream. I'll keep this in mind. Oh, it's a TED Talk. Oh, it's pretty short. Okay. That's super interesting. Can't get enough of his lectures. Yeah, he's got really good ones. No, I needed a break, and like the thing with these problems, like, so I've kind of just got like a lot going on right now, and I'm in like basically I'm trying to like take a break from like thinking like I'm like overthinking a lot of stuff. I don't want to go into too much detail here because like some of the people that this affects might see the stream and like publicly be, like I don't want to mess up certain relationships I guess I have, like, both professional or otherwise. Sort of something like that. Like I'm thinking about a lot of different things, and I'm like, I've kind of already said too much on the channel, but I'm sort of avoiding talking about it. But basically, there's like a lot of changes going on in my life right now, and like they're all at like different times. So like some things are gonna happen like all together in like a week or two, and some things are not. I have to wait, and like there's all kinds of stuff going on, and I'm just kind of like I need a break. So, but no, I'm not. These problems that I'm solving, like I kind of just want to solve all of them because like I had set this goal to do that a while ago, and I kind of just want to be at that point, and it's not going to be for a job anymore. I probably am not even going to work as a software developer anymore. First minute is him explaining in detail of what he would do to Hitler. Oh no. Well, that's a really interesting question. Actually, I have kind of a sequence of thoughts regarding exactly that subject. Actually, just while we're talking about it, I want to go over that because basically it goes like this. People ask like, why do, like, if God is so good, why do horrible things happen to people, right? Especially babies, right? Specifically babies, right? They say like, why do horrible things happen to babies if God is so good? And I thought about it, and I was like, well, one of the things that came up in my mind is like, well, if you knew a baby was Hitler, right, would you murder that baby, right? And a good number of people would probably say, yeah, I would. And then you say, well, maybe so would God, right? If you knew this baby was really evil, maybe that's the case as well. And actually, the truth about our nature is that when it comes to sin, every human being is going to be like a mini Hitler. We're all going to do things that are unfair and evil, and in the eyes of a perfectly holy and just God, none of it is acceptable. So basically, nobody on earth is innocent. And the only difference, not the only difference, but one of the differences between Hitler and everybody else is that Hitler had the power to act out on all of the evil things that he was thinking, and did it. Whereas a lot of us don't. One, we don't have the power to do it, and two, some of us have some constraint. And then some of us further still are Christians, right? So we actually really try to restrain it. I kind of thought about that, and I was like, because that's a complaint you get from time to time about like questioning God. If he's so good, why do horrible things happen to babies? It's like, well, if Hitler, what would you do to Hitler, and then what would you do to Hitler if you knew he was a baby and you knew it was going to be Hitler? Like, what would you still do those things? And I think a good number of people would say, yeah, they'd basically murder the baby. It's like, okay, well, maybe God would do the same thing. You don't know what you actually you do. We all do know that children will grow up to be evil. We know that. And we know that's what they're going to do. Maybe not all the time, but they will be. Another way also to understand about like everyone having a broken moral standard, just while I'm on the subject also, is like if you think about everything you ever complained about in your life about other people, like every judgment you made about another person, and then you tried to apply it to yourself, you'd find that you couldn't you couldn't even be morally righteous in your own set of rules, much less God's rules. And how horrible it would be if you were the one who got to decide who did or didn't go to heaven based off of your own standards, because you wouldn't even make it. And that's pretty much true of every person alive, every person that's ever lived. My view on humans is that we are a super cruel species. Without being sculptured by society or religion, we're going to be horrific thieves. There's also mental disorders that cause a lot of evil. Yeah, no, I agree with you. I'm grateful. I'm grateful that you hold that view. That's actually the biblical view. Is that exactly? We were originally given the choice to be with God in the Garden of Eden. All we had to do is be obedient. Just one tree with one fruit. Just don't eat it, and basically you're in paradise. And then Adam, our father, was sinful, and he allowed himself to be persuaded to do evil, and he ate that fruit, and so we were cursed since then. Then all of us are descendants of Adam. We all have the same curse, and we all have the same sinful nature. That even in paradise, where all you have to do is just not eat this one fruit, we would still throw it away for our own apple nom. We do it for our own selfishness. So that's how we are. That's what we are. And the Bible talks about that quite a bit, about the heart of man. And yeah, again, I think you really, all it takes is just looking around really to know that, like, okay, human beings are really evil. But the hard part is looking at yourself and admitting that you are also yourself evil and have done things that you shouldn't have done. And then, what's the answer to that? Am I gonna? Basically, the question is like, well, if I did all these evil things, if there's a heaven, which I know that there is one, but for someone who doesn't know that, asking the question, why would they let me in, right? and then that gets you kind of thinking about God and the Christian answer to those questions. Yeah, like really short succession. I think the gospel is we've all committed sins. We've all fallen short of the glory of God. We all deserve to face the wrath of God. Because of that, perfectly holy, holy and just God can't accept any of that. Can't go to heaven because of that. So what God did for us, so that we don't have to take His wrath, So he came to earth as man, as Jesus, fully God, fully man, died on the cross, was murdered. In those 3 hours, or a few hours, I don't know how many hours exactly, he took all the wrath of God upon himself for our sins. He died, was resurrected 3 days later, conquered sin, conquered death, showed us that he's God, showed us that he's conquered death, and had 500 witnesses that he was resurrected. And because of that, and what we're asked to do now, it's a gift from God that our sins are forgiven. All we have to do to accept that gift that was given to us on that day is, or on those days during that time, is we need to repent of our sins, so to not do the evil things that we've been doing, and to believe in Jesus Christ, believe that he's God, believe that the things that he did die for our sins, that he did also the things that he said about sin, what is and isn't sin, to believe those things as well, and not make up our own, twisted idea of what is and isn't right, what is right and what's wrong, right? Because that's what most people do. They think that they're not evil because basically the evil things they do, they say, well, that's not evil because I said so, more or less. They come up with some reason why this is evil or not evil, and so they all they all are like, yeah, I'm not evil, I'm a good person. Did I lie? Did I cheat? Did I steal? Did I fornicate? Did I hate somebody? Was I jealous? Yeah, but I'm still good. But which, by the way, hate is murder of the heart, right? So actually, that's murder. Not that most people don't murder somebody, but some people do. I mean, it happens. Some people do that, and they still think that they're not evil after doing that, which is crazy. I've actually seen that recently. I was watching documentaries of like criminals, and I saw one guy who shot and killed someone. And he basically, the trial, he was claiming self-defense. So in his mind, genuinely, he thought that he didn't do the wrong thing. But he killed the guy, and it wasn't in self-defense because the guy was like, he didn't need to kill him. Like the guy did attack him. So guy A and guy B, guy A being the one that went to jail and murdered guy B. Guy B attacked guy A, but guy B didn't pursue him. He just pushed him to the ground. So, did you know that you can basically guess someone's sex based on a certain part of their brain? And that's what caused a lot of transgender stuff. It's the equivalent to someone being born in the wrong body. Let's hold off on that one. I don't want to respond to that. I have to say, when it comes to the transgender stuff, like, let's just say I have, I think I've said it a few times, like I take the biblical perspective, right? So, yeah, it's from Robert Sapolsky himself. Yeah. Because I figure it's probably from him on people before transitioning and after. Yeah, and old people who never did it. Right. So, like, I agree that there's structures in the brain that are related to gender. They all have it in common. However, let's just say, I appreciate when you bring it up to me, and I'll look into it. I'll take a look at what Sapolsky has to say about it. But like my official position is basically, the biblical position that transgenders, basically it's a sin, right? It's a sin to be transgender, so it's fine if you don't believe in it. I mean, I believe in like the observable science, right? Like I believe in that. Like I believe that you can basically, if you like get a guy and you jack him up on female hormones, like he's gonna become more effeminate, and vice versa. If you get a woman and jack her up on testosterone, she's gonna become more masculine. Like I do believe your body has, biological structures that more or less control aspects of your life, whether it be male or female. There's the XY chromosomes, right? Like I believe these things, but I also have to be very careful around that subject because, like I said, I believe. Not only do I believe it's a sin, but I also think that there's a lot of like excuses that are made that are not. I can't really support those things. I can't support excuses, and I can't give credence. I guess I can't like tacitly approve of certain things. So I have to be very careful. I just have to say I take the biblical position, but as I said, I do believe in the body having a certain degree of control over these things. If you want to listen to what he says, 12:30. Yeah. Actually, hold on. I do want to know what this is. Oops, I need to do that. I actually do want to see, because I said I'll check it out, but I want to. It's not V, is it? It's question.v, right? Oh, hold on. What is? Let's try again. There we go. Okay. Pain Summit? Keynote didn't allow the recording of presentation, but has allowed the sharing of the Q&A. Interesting discussions. Pain? Ouch. That's a heck of a name for a conference. Okay. I'll have to save this somewhere, I think. I don't know if I'll be able to find this again. The Pain Summit, San Diego Pain Summit, okay. Maybe I could bookmark this. I'll do. There actually is. There we go, watch later. Whoops, I need to do that. I keep pressing the wrong button. People ask him questions and he responds. Gotcha. Okay. Yeah, I'll have to look into that. I don't know when I will. I know I say I'm going to, but I don't know when I actually will. But that'll keep in mind. What was the other one you sent? You said about, I'll say this one too. I do spend quite a bit of time on YouTube, just watching things. We'll do. I'll say this one too. Thinking if I could figure out a way to maybe alleviate this one portion here. If I could maybe modify the base case slightly here, then I'll probably take a break and go to bed. Let's see, this left and right. 1, 4, 9. This shouldn't be 2. This should be 0. Wait, why is this b squared? Hold on a second. 1 plus 2 plus 3 plus 4. Oh no. Oh, maybe it is supposed to be 2. What is 1, 4, and 9 supposed to be? Well, 1 through 4 we could check right now. 4 and 9. What do we get? That should be wrong, right? Can't imagine how strange humans start to look for him. Since all he does is study behavior. And etc. He talked about that too at some point. Yeah, I heard him describing, like, if he sees a really big guy, he's got to resist the urge to, like, try to shoot him with a tranquilizer, because a guy that looks like a gorilla. So that was pretty comical. So 4-9 output true should be false. Oh, so 4-9 should be 0. Interesting. So let's look at that as well. 4 and 9. And we get to hopefully get to the root of the problem here. Okay, let's see here. Oh yeah, it's pretty funny. It's pretty funny. So 117 we get left, right 0. The right is 3, 4, and 7. So and there's another left, right 1, 2, and 6. That should be 0, and then 4, 4, and 6 should be 0. But maybe I'm just wrong about this being a Sprague-Grundy, being an impartial two-player game. I don't know. I think I'm just doing something wrong. I don't think I'm. Part of me thinks it'd be really hard to do this otherwise. So actually, we get 0 a few times for this 149, but the expectation is actually a false. So it means this should be 0. This 49. Neither of these come out to be 0, but these left and right solutions come out to be 0. 117 is 0, which I think is true. And then 347 is also 0, right? If you choose 4, then there's 3 left and 3. If you choose 3, then it's 4 left and 4, means the opponent is always going to win. Yeah, both of these choices, the opponent wins are 1s. So this should be 0. So both of these should be 0. But why 1, 2, 3, 4, and 9? That's really confusing, right? It's kind of hard. 149. Just thinking here. Yeah, so this is saying that this is a false. This is a false. But that's not correct, because you could go 1, 4, 2, 3, 4, and 9. You could pick 2, and then now you have 7, and your opponent has 1, 3, and 4 to pick from. You know what? Maybe it's not. Maybe it's not an impartial game, or at least it's an impartial game, but the way that I'm defining this is wrong. These aren't independent games. Actually, you have to consider the game with all the pieces involved. I think that's the part that's wrong. Or maybe you need to subtract 3 and 4 from 7 and consider 1 without 3 and 4, and then similarly subtract 1 and consider 3 and 4 with 6. Maybe that's what I'm doing wrong. That could be it. That actually might be why. Maybe, yeah. Okay, I think maybe I have the whole thing wrong, or a significant part of this wrong. Yeah, these aren't independent. I think. once you select 2, then if you only had 1 to pick from and 7 left, then obviously it's like that's not possible. And if you only had 3 and 4, or rather, that would be not possible. And then 3 and 4 also. The player would never win looking at 3, 4, and 7, because the next player is always going to win. So actually, so that means that selecting 2 would give you the wrong answer that the other player can never win. But the other player can win from here. The other player can pick 1, and then they pick 1. So now it's at 6, and now anything you pick, if you pick 4 or 3, they win. So 2 is no good. If you start with 1 and they're presented with 8, they could pick 2, and then you have to pick 4 or 3, and then they win. If you pick 3 and they have 6, then they could pick 1, and then you have to pick 2 or 4, and they win. If you pick 4, then they could pick 1, and same deal, you still lose. So you lose in every case. I think if you split this into 1 and 0, and 3, 4, and 6, and consider those to be separate cases. Maybe that works. No wonder this is so much harder, because I had the wrong idea. Yeah, the coding part is really supposed to be pretty quick. If you have the wrong idea, then the coding part will take forever. But if you have the right idea, the coding, you only find a few errors here and there. It really shouldn't take too much time. So really, this is an issue of having the wrong idea. But if you try to pick 2, and you try to take 1 and so you subtract 7, and you subtract 2, subtract 2 and 7, 1 and 0. This, I think, we should say I'm actually not sure if this is 0 or 1, what this should be. I'm not sure. This other part, though, should be processed normally, right? And it would be sort of break down into 4 and 3 and 3 and 2. 4 and 3 and 3 and 2, and then 4 and 3 and 3 and 2, and then so is this positive or negative, or is this 0 or 1, right? So for the player that's looking at this, you can't win. This is a 0, because you can win here and you can win here, and so that means you won't be able to win here. This is a losing position here, right? No matter what position you pick. Yeah, so I don't think that what I'm doing here is correct, because these aren't really independent games. Because just because you, like, if you do 1, 2, 3, 4, 5, and you select one of these, considering this side and considering this side separately doesn't really make a lot of sense, because you might have a consideration of like 1 and 5, for instance, and your total. Like, you don't necessarily immediately remove these other values from the total and remove them from consideration. That just doesn't make sense. So I think this whole Sprague-Grundy idea doesn't really work so well this idea is wrong. This original idea, which I thought about hours ago, is just incorrect. You can't just split this up into consecutive integers and XOR them, the Grundy values, unfortunately. Doesn't work like that because yeah, the game is a little bit different, I guess. Now, you could go through all the different choices recursively and take the Grundy values of each choice. And then just do basically, that might be what I was supposed to do. S of S difference this set alpha T minus alpha, and then, you know, take the union of all these different alphas, the mechs of all of these. Not max, but mechs. And this is for every alpha of S. Actually, I think this is not that bad. This is probably fine. This set has 2 to the 20th different values, and then T has T values, so you can do 300 times 2 raised to the 20th. I mean, that's still kind of expensive. We can memorize this. I mean, this will be correct too, I think, but this is not very efficient at all. This is actually like really expensive. I also don't see how this could be much better than what I was already doing. This feels a lot like the same thing as the brute force solution. I don't know. I'm kind of stuck here. But are these independent of each other? Like, I'm wondering if these are independent games. I'm wondering if I should take the sum of these independent games. And take the XOR. I don't know what the value of that is, though, actually, realistically. Because it's still a linear. No, I don't know. Yeah, I don't really know. It seems. I don't know, man. I don't know. I don't know what to do here. This is a little bit awkward. Well, I mean, really it's only by 210 instead of 300. 220 million is a lot of executions. Like if it takes like 4 milliseconds for 120,000, then what's that? We invert this. somewhere around here of a 1 over, oh there it is. Multiply this by whatever it was, 2 to the 10th to the 20th times 210. That's 1843 times 4 milliseconds. That's gonna time out. That's gonna time out. That's 7 milliseconds. That's 7 seconds. Yeah, we only have 2 seconds, roughly. A little over 2,000 milliseconds to work with. I could maybe memo-wise the solutions, but I don't know if that really helps that much. If that actually helps that much. I don't know, man. I was so eager to split the sets, and to try to make use of this, but that's not correct. It's wrong. I don't know, man. I mean, maybe I could just code that up quickly before I go to bed. Should only take me a few minutes. But yeah, this is wrong. So that's why it doesn't work. Okay. Let's try something that seems correct. Base case is probably same deal. Actually, it's not A or B anymore. It's actually just a set. And we'll say vowels. And then I don't know if we need this anymore, really. Probably don't. Probably won't. We're going to say we don't really have this high-low anymore, or this A-B. It's less than or equal to 0. I'm not sure what the base case is going to be. Come back to that. Set of values. I mean, yeah. Do you get a new set for each? Well. Oh wow. Okay. Huh. This is not very good. No, you actually just end up with exactly what I was doing before, where we're just doing a brute force solution, because this mex function isn't much better than recursively. Excuse me. No, this is going to be too inefficient. This mex function isn't much better than just taking the an or an and over all of the values. Actually, exactly what I did before, where I just simulated the game. Is going to be the same thing, except this will be, I guess, less efficient. It's actually going to be a little bit less efficient for the Grundy values, the Grundy values. I'm wondering if maybe calculating these Grundy values, if there's a pattern. Maybe that's what I'm looking for, is some kind of a pattern. And if there's a pattern, then I can exploit that pattern and solve this very quickly, very efficiently. That might be actually the approach. So maybe just keep brute forcing it and look for a pattern. Yeah, I mean, find some periodicity in the Grundy value, something like that. Yeah, because I think if I use Grundy values to try to solve this, it's going to be exactly the same thing. Because I'm looking at the set that I'll be using, the different sets, and because we're doing this recursively, we can actually do it using using that backtracking algorithm that I had before. But it's just the same algorithm I had before, with terminating early with terminating early with what's it called? Excuse me. Yeah, instead of using sort of zeros and ones, we're going to have the Grundy values, which will be slightly different. Man, it turns out to be a much more challenging problem than I was expecting. I mean, I think part of the issue is trying to figure out how to break the problem into independent games. Maybe I was right actually about this, where maybe I can use these independent games. Maybe it is okay to remove this value and take this XOR from the total. I think if you can't, I think it's too hard otherwise. The reason why I'm thinking maybe you can do it this way is that I don't think you can, but they're not independent games. That's the problem. They're not independent if you use a consecutive, yeah. It doesn't have to. They don't have to be consecutive. No, it doesn't. No. I don't know. I don't know how to make. I don't know how to. I don't know what to do here. I don't know. Excuse me. Yeah. You can't break these into subproblems like that. I don't think so. Sub games, you can't really do that. Maybe you can. I don't know. Because you can select these values any order that you want. I think the reason why it's hard to make them these sub games this way is that assuming that you selected all of them at once, I think doesn't make a lot of sense. Yeah, I don't know. Excuse me, maybe Grundy is not what I'm supposed to be using here. I think I should go to bed. I don't know, man. This is super strange. What could this be, this problem? What could it be? There's got to be some kind of a pattern or something that I'm missing here. Something going on. Hmm.
Excuse me. I wonder if there's a recurrence relation that I'm missing. I know that I do know that if you select one of these numbers, from 1 to n, then the numbers from left to right, excuse me, kind of form like something of a subcase, but you still have numbers on the right side to work with, to think about. So I don't really know. I don't know, man. It's a tricky thing. There's got to be some kind of a pattern or something. There's something here. Something's not right. Something's kind of funky. It can't just be the simple. It can't just be the brute force. And the Grundy theorem doesn't seem to be helping that much. I think I'm just gonna go to bed. I'm kind of frustrated, but yeah, this part's not right. That doesn't actually work. Man. It's gonna bother me, this question. This so closely resembles a two-player impartial game. I think it is a two-player impartial game. It's just the number of states that you're working with here is enormous. I think that's the problem. It's absolutely gigantic. It's 200 million states. Yeah, because each state has another set. Has another, basically a subset of 1 to 20. It's every state, and then every one of those states also has an associated total. Yeah, there's probably some relationship between the set, the Grundy value, I guess the subset, the Grundy value, and the total. That's kind of revealing, I suppose. I mean, maybe I'm supposed to just do the DFS, but use some
use some degree, some amount of pruning. Maybe this is actually really simple. It's supposed to just prune certain things, but you can do some pruning here. You can keep track of like the sum and the sum is smaller than the number you're looking for. And you can stop right there. Actually, I think that pruning alone might actually push us into the range of acceptable time bounds. I think that's what I need to do. I need to just focus on the DFS and then just add optimizations. I mean, I guess it was nice to look at Grundy again, but didn't solve the problem. I don't know. I'm like so tempted to just go back to the DFS. Let me see. I think I should go to bed though. Getting tired. Let me see if I can pull this up. Oh wait. I need to say hold on to this. Just give me just a moment. It's a good thing I saved this. It's a good thing I saved this. I want to go back to back to basics. I don't want to use bits for the current value, so I want to use actually the set itself. I want to use an unordered set and loop over the unordered set, and but I don't want to. Yeah, I think I had it right the first time actually. I don't want to, when I was using a regular set, I want to use the unordered set, but I think it's better to use regular set, use ordered set, because the ordered set I can get where I inserted the value. The problem with an unordered set is you could end up in like something of an infinite loop, I guess, as you sort of add and remove values. So let's use a set. And we don't need this part either anymore, this LSB. And we'll say maxent, I don't know. S dot, we can keep track of a sum too. Current target. I don't know. S dot current vals dot or begin. If this is greater than or equal to the target, then we return whether or not we're the first player or the second player. Let's have a sum as well. Running sum. Excuse me. I actually don't think it's going to take too long to calculate. We're going to make it easy. If it's running sum, we're just going to plus equals I. Well, actually, we don't need to do that. We can make it a what do they call that? A formula, a calculation. One line of code. Yeah. So. And then we can say this is the other side. So if the running sum is less than, this is another pruning thing, less than the current target, and that means whoever's playing here can't win. Yeah, player 1 can't force player 2 to do anything at this point. Player 1 can't win, player 2 can't win, no one can win. So that's sort of that's extra little bit of a prune here. Big, actually probably a big prune here. So we're going to say auto p equals s dot current vals. Begin p is not equal to s dot current vals dot end plus p. S dot current is going to be minus equals p. Say val equals p. Current vals dot erase val. Check possibility. Player to true. Current vals dot insert val auto insert pair. Set p to the insert pair dot first. S dot current plus equals val. Check possibility, return true. Otherwise return false. I want to do pretty much the same thing on the other side here. Except this is inverted. This is true, false. And then we want if not check possibility, return false, return true. Yeah, we could probably, this code is mostly duplicated except for a few parts that are sort of toggled between, depending on what the S player is. So we probably could actually put this in one loop and then just modify this S dot player depending on what this was when we called this. So this goes from false back to true if this was initially true, and this goes from true to false if this was initially false. So really it's just a toggle and a toggle. I think these are both just toggle. and then over here, here and here, I think we can modify depending on what S player is. So if S player is false here, then we want not the possibility. And if S player is true, then we want the possibility. And false true and true false. This also toggle depending on the player, which ones we return. Pretty interesting. Could probably rewrite this without yeah, could probably rewrite this without all of the if then else's and all of that, I guess. So let's remove this part now. Alright, what happens if we run this code? Does it compile? Oh, it's correct. Okay, so it's correct for the inputs we gave it so far. Let's see if we give it something, some other inputs. It's pretty quick for those cases. Alright, this one should break it. This one was one of the ones that we almost broke on before. TLEs. Okay. Wow. So actually the bit version of this was pretty quick. Whoa. This is a lot slower. Whatever I did, this is a lot slower. I forgot to add that part of the logic that was supposed to make a difference. Wow. This is way slower. Whoa. It's like 10 times 20 and 60. Huh. So this is a lot less efficient. No kidding. Wow. Wasn't expecting that. Interesting. I guess that makes sense. Oh wow. I made things a lot more efficient with my changes, but still not enough. I'm wondering if I prune with this running sum, if that'll do anything. That's kind of what I was looking for before. Let's see. Let's go back to this one then. So this one's really slow. So this one's not as. This one here is way more efficient. Wow. Huh. Huh. 4 milliseconds, whereas the other solution almost times out, right? Zero milliseconds. What is going on? I mean, I'm not complaining, but alright, this is super efficient. Way faster. 36 milliseconds. And we're getting there. We're getting there. Alright, there we go. That's 10 times now. Okay. So we go to 20, 120. Still 416 milliseconds, okay. How about 130? TLEs. What about 121? Whew. Alright, let's try running some, see if this helps at all. Okay. So as we subtract values, update our running sum. And target running sum. Have over here target running sum. Hmm. I think I always return false here. Oh, that's so much slower now. Just that one if else here. I'm wondering if I could push this all into one for loop rather than an if statement, and then if this will make it fast enough. That made it so much slower adding that that running sum. If the running sum is less than the target, then you're always false. I made it so much slower. Wow, that actually didn't help. Maybe, no, probably not. No. I don't know, man. I really need to go to sleep. I really need to go to sleep. Wow, that was 700 milliseconds. No kidding. Huh. Alrighty, so we could take this, I guess. There's no way though. There's no way we speed this up that much. What is going on? Why is this? Okay. So here, the player is true, so you return check possibility as dot player, and then not possibility player is false, return false. Here return not player. And then you have one more detail, which is not check possibility. If the chair, if so, if the player is false, I would say s.player. If that player is true, then you want check possibilities. Or not s.player and not check possibility. Something like this. So if the player is true, then you're checking for the possibility. And you return true, terminate early if it's player 1. If it's player 2 though, where it's false, then you're checking this case. Something like this. Let's see what happens. Oh, still correct. Sweet. Quite a bit more efficient, huh? Can you believe that? It's shaved off a few milliseconds. Oh, not too many more. 700 milliseconds. 900. Not much more efficient, but a little bit more. They're both about the same. It doesn't, you don't really get very much by modifying this. So I really need to prune more somehow. Actually, this seems to be slower. After making these changes. Starts to TLE. I don't know, man. How do I make this more efficient? 360. Interesting. That is a tough one, huh? Hmm. Hmm. Whoa. Did that say 222 milliseconds before? So it was 1,000? This one is rough. 122. Reasons unbeknownst to me, this one goes very slow. It's like 1,000, and then if we go here, it's actually faster the first time I did it. Alright, never mind then. I mean, I haven't got a clue. I haven't got a clue. So here's a question. Do I even need to check these? Oh, I think probably do. Yeah, you need this base case. How do I... That's all I got, man. Sure this is correct, but it's too slow. This is a brute force solution. I just gotta go to bed, I think. I think I might give up on this problem. Spent a lot of time on it already. Hmm. I don't know, man. I'm thinking what we gotta do is basically try to find some property, the Grundy values, that we could exploit. I think that's the only way to do it. Actually, rephrase this as Grundy values, calculate those values, and then reframe this as Grundy values, look for a way. Just print out a bunch of them, look for a pattern, some kind of a pattern, the Grundy values. I don't know if we have another way to do this. I don't think so. Can't really brute force it. Or at least if you can, I don't know how. Alrighty, I'm gonna go to bed. This has been an interesting question. Yeah. I think I saved this. Okay. Close that and close all this. So yeah, thank you all for watching, hanging out, saying hello. Do appreciate it. I'll talk to you all soon. I'm gonna get going. I'm falling asleep over here. It's time for bed for me. I'm past my bedtime here. Yeah, I tried. I didn't really get there. Tried, didn't really get there. All right.